Hello students, I am Akash Gupta again and I welcome you all on PhysicsWallah English. We are going to cover today the modern physics. Modern physics is a very important chapter for every exam that you are going to face. Even in board exam, in term 2 exam, this lecture or this chapter may give you 11 marks, but just by covering this lecture and a little study of NCERT can give you 11 out of 11 marks in modern physics. I have given you two more lectures, ray optics and wave optics. They can give you 17 marks, and my next lecture on semiconductors can give you 7 marks. So cover these 4 chapters for your term 2 and read NCERT, and you can score 35 out of 35. There is no doubt about it. Okay, so let's begin. In this chapter, we are going to discuss the photon theory of light and matter wave. That's a very small chapter, but still it may give you at least one question in every exam you are going to face, right? Then we have photoelectric effect. Then we have atomic structure and X-rays. Photoelectric effect and atomic structures are not very new to you. You have studied them in chemistry also. X-ray is a little new. And nuclear physics and radioactivity, this too you have studied in chemistry, and we are going to revise it. So by studying this lecture, I'm sure you will be able to grasp each and everything, because this is almost a revision of what you have studied in chemistry. Okay, so let's begin. Let's not waste time and let's begin. So the first is photon theory. Okay, what is photon theory? Okay, we all believed that light is made of corpuscles, means light is made of particles at the time of Newton. But after the Huygens theory, after the study of interference of light, after the study of diffraction of light, people started believing that light has wave character. So light has wave character. But in 1900, in year 1900, and specifically speaking 1905, Einstein demonstrated the photoelectric effect, and the explanation of photoelectric effect is not possible if you do not believe in particle nature of light. So these experiments forced us to believe that light has dual nature. Light has wave nature also. Light has wave nature because it exhibits interference, diffraction, polarization, and this is the sure proof of that light has wave nature. But the light also has momentum, and momentum is a characteristic property of particle. Light carries momentum and it exerts pressure and force on the surface it strikes. So light also exhibits particle nature. Okay, so light has dual nature. It has wave nature and it has particle nature. So that's amazing, isn't it? Okay. That is called quantum nature of light. Light is made of, like we believe, light is made of tiny discrete particles. Okay, and these tiny discrete particles are called photons. These are called photons, and they have both. They have a little energy in them and they have a little momentum in them. So what we believe is light particles are a tiny energy packet called photons. They have a little wave in it. So this is a photon. Nobody has seen photon. I'm just drawing photon on the basis of my imagination that it has a particle and it has a wave in it, right? So they have energy and momentum. Okay, a light photon, if the frequency of light photon is nu, its wavelength is lambda, then after many studies and experiments, we found that the energy of photon is given by hc by lambda, or h nu. I think you know, h nu means sc by wavelength, or h times the frequency, right? And the momentum, as light is a wave, it carries energy, and energy is given by this. But this is the energy of one packet of energy, one photon of energy. And the photon also has momentum with it, and the momentum is given by energy divided by speed of light. If you put energy equals to sc by lambda, you will see the momentum equals h by lambda. You should also know that h is a Planck constant here. H is a Planck constant here, whose SI unit SI value is nearly 6 times 10 to the power minus 34, and C is the speed of light, which is a famous 3 times 10 to the power 8. But the multiplication SC, obviously you can find the value SC in SI unit, but SC is also equal to 12400 electron volt angstrom, or 1240 electron volt nanometer, right? So if energy is required in electron volt, right? If energy is required in electron volt and we are given lambda in angstrom, we have to use SC, the value of SC as 12400, right? And if lambda is given in nanometers, then use SC as 1240 electron volt nanometer. So this makes the calculations very easy for us. Okay, so remember, there I've made 2 points here. The energy of a photon is SC by lambda, or h nu, and momentum of photon is E by C, energy upon speed of light, or h divided by lambda. Okay. The next we have power of a point source. Okay, what is a source? The source is actually object, a tiny object that emits light. Even the sun is a light source, the tube light is light source, but by point source we mean that we have a tiny particle like source which is emitting light in every possible direction. Suppose the light being emitted has an average wavelength lambda, or all photons of light have wavelength lambda. Then if all photons have same wavelength lambda, the source will be called monochromatic source of light, because it is emitting only one kind of light, only one wavelength of light, right? So the energy of each photon is definitely going to be SC by lambda, and if this source emits n naught photons, n naught is the number of, say, photons emitted per second. So if n dot is number of photons emitted per second, so each photon carries this much energy, SC by lambda. So energy emitted per second would be actually the power of this source, and this power is given by n dot SC by lambda. We can also write it as n dot h times nu. So this is actually the energy. It is actually the energy emitted by source per second, or power of the source. Okay. Next we can talk about the intensity of the point source. Okay. As you know, the point source emits light in all directions equally. Okay. So if we have a point source right here, and it is emitting light photons in every possible direction, not only in 2 dimensions. This is emitting light towards you also, it is emitting light backward also, means in 3 dimensions, in every possible direction it is emitting light equally. Then if, say, we want to find intensity at a distance r from the point source, if we want to find intensity at a distance r from the point source, obviously when one wave reaches a distance r, every photon emitted by the point source reaches a distance r, and they basically fall on a sphere of radius r whose center is at the point source. So as intensity, the chi is defined as energy falling per unit time per unit area. So as we have power P, if we divide power by area of this sphere, we can get energy at a distance r from the point source. So as power is n dot h nu and area is 4 pi r square, you all can see as we move away from point source, the intensity falls as 1 over r square. The intensity here is intensity falls as 1 over r square. And you can also see the intensity is proportional to number of photons emitted per second. Intensity is also proportional to number of photons per second. So if you double the number of photons, if somehow we double the number of photons emitted per second, intensity is going to increase. Intensity is going to be doubled if the frequency is kept constant, because intensity also depends upon the frequency, right? So this is intensity. Okay, so we have a simple question as in NEET 2021 and the question is the number of photons per second on an average emitted by the source of monochromatic light of wavelength 600 nanometer when it delivers power of this watt will be. So basically, as we already know, the power is n dot. N dot is number of photons emitted per second, right? And times the energy of one photon, as we are given the wavelength as 600 nanometer. So energy of one photon can be written as Sc by lambda. Now n dot becomes n dot equals this p times lambda divided by hc. Now put values of p as this, lambda as 600 times 10 to the power minus 9 because we have to convert them in meters, h as and c, the value of h and c you already know, you can just flip a few pages, and in the paper also they give the value of h and c, and if you put all the values, the value of n dot is going to be nearly 10 to the power 16. So that's why C is your perfect choice. That is your answer. Let us see what we have next. So now we are going to study a new concept, which is matter wave. After theory of hydrogens was proved by Young's double slit experiment, diffraction experiment, polarization experiments, we believed, everybody believed, light is a wave. And if light is a wave, then Einstein demonstrated that light has particle nature, that light has both nature, light has dual nature. So de Broglie had a new thought. If light, which is a wave, can have particle nature, why can't particle have wave nature? Because nature loves symmetry. If one concept has two characters, why not the other concept has the two characters also? So de Broglie hypothesis, it is called de Broglie hypothesis. He hypothesized that every material particle like electron, proton, neutron, and every material particle like the ball, the cricket ball, the tennis ball, every matter particle, every material particle is associated with a wave. Like light is associated with the particle nature, every particle is associated with the wave, and this wave is called matter wave. It was just a thought given by de Broglie, and this wavelength of matter wave is given by, he said, the wavelength of matter wave is given by h divided by momentum. He just used the same formula for momentum of light, which was momentum equals h by lambda. So he thought, if light has momentum, why can't matter particles have wavelength? And he just transferred these two and he got the formula like lambda equals h by momentum. It was just a thought. Okay, but later, after experiments of Davison and Germer, it was proved that particles too have wave character. In Davison-Germer experiment, it was proved that electrons exhibit diffraction. So particles have wave nature. That is why they are showing diffraction. So it was later proved that the de Broglie was perfectly right, and his formula also matches with the results obtained by experiments. Okay, so now we believe the de Broglie wavelength lambda d, let's say de Broglie, always remember this is not a wavelength of a wave, it is wavelength of a matter wave. It is a wavelength associated with the matter particle like electron, proton, neutron, alpha particle, etc. So this is a wavelength associated with matter wave or a particle, and this is equal to h upon the momentum of the particle. Okay. We also have few other formulas like lambda de Broglie equals h divided by momentum. Momentum can be written as square root of 2 times m times kinetic energy of the particle. So this is another formula for de Broglie wavelength. If you have momentum, use the first one. If you know the kinetic energy, because in many situations we know the kinetic energy of the particle. So if you know kinetic energy of the particle, we have to just find kinetic energy of particle, and we have to find lambda d. Use this. You can also write, if you know mass and velocity or speed separately, lambda equals h upon m times v, where m is the mass of the particle and v is velocity of the particle. Always remember the p here is magnitude of momentum, because the wavelength is a scalar phenomenon. So we have to write magnitude of momentum here. So lambda equals h by magnitude of momentum of the particle. Okay. There is something we should study. Okay. How to give momentum to particle. So suppose we have certain ways. If we have a charge q and it is accelerated by a voltage v, the work done on the charge would be q times v, and this work done is converted into kinetic energy if the charge was initially at rest. So this is equal to actually kinetic energy. So if they ask you what is the de Broglie wavelength of a charge accelerated by a voltage v, we have its kinetic energy, and now we can use this formula to find the de Broglie wavelength of this charge, and the de Broglie wavelength would be lambda d equals h divided by square root of 2m times kinetic energy and 2 times mass of the particle is say m, and kinetic energy is q times v. If we have an electron in the place of that charge q, obviously the kinetic energy becomes E times v, and lambda d becomes h divided by square root of 2 mass of electron, charge of electron, and voltage. But if we have an electron, we know the mass of electron, we know the charge of electron, we know the Planck constant, only the voltage will be unknown and will be given in the problem. So if we place all the values of h, m and e, remember this is a very important point. If we place all the values and convert this into angstrom, this is equal to nearly 150 divided by V angstrom. So here you have to say this is only valid for electron, because at the place of mass we have placed mass of electron, at the place of charge we have placed charge of electron. So this formula, this is valid for any kind of particle, for alpha particle, for proton, doesn't matter, but this is only valid for electron. If they say you the electron is accelerated by a voltage V, so put the voltage V in volts here, and square root of 150 by V gives you the de Broglie wavelength of that electron in angstrom. Remember this. Okay, next point. Say we have a gas molecule in a sample of gas at absolute temperature T. So if a gas molecule is at an absolute temperature T, its translatory kinetic energy, its average translatory kinetic energy is actually 3 by 2 times of Boltzmann constant times absolute temperature. I think you all know this. Okay. So if kinetic energy is this, average kinetic energy is this, the average de Broglie wavelength, remember, average de Broglie wavelength, let me put an average sign. This is an average sign. So average de Broglie wavelength can be given by h divided by is square root of 2 mass of the gas molecule times average energy, which is 3 by 2 kT. So 3 by 2 kT. 2 cancels out and this becomes, let me write it again. Yes, it becomes 3 Boltzmann constant times T. So this may be a variation in a question. Okay, now last. If a charge is revolving in a magnetic field B with radius R, you all know that if a charge is revolving in magnetic field with radius R, the radius arc is given by R equals mv by qb. So the momentum mv becomes r qb. If you are given the radius, the charge and the magnetic field, the momentum is r qb. And this time if they ask you what is de Broglie wavelength, the de Broglie wavelength would be h divided by r qb, because it is h by the magnitude of momentum. Always remember this. So these are the few variations on which the problems can be asked in different examinations. So let us see what we have as first question. So we have an electron of mass m with initial velocity v naught I cap. So we have an electron traveling towards positive direction of x-axis. V naught is positive. Okay, and it enters an electric field. An electric field is directed towards negative x-axis. Okay, so say this is y-axis, this is x-axis. The electron's velocity is v naught, and electric field is E naught towards left. As electric field is towards left, electron experiences a force towards right, and because of this force, it experiences an acceleration towards right, and that acceleration becomes EE by m. EE not by m, because acceleration is force divided by mass. If this is the acceleration, the velocity after time t, what would be a velocity after time t? So velocity after time t would be initial velocity v naught plus acceleration times time. So we have E naught by m times t. This is the velocity, obviously in x direction. And they are asking us what is de Broglie wavelength after time t. So obviously the de Broglie wavelength after time t would be it would be h divided by mass times the new velocity, right? The new velocity is magnitude. Okay, if you just take if you place v here and take v naught common, so mv naught, it becomes 1 plus e naught t by m v naught, and obviously h divided by mv naught, you can replace this by initial de Broglie wavelength, which is lambda d here. Okay, so lambda naught here. So this h by mv naught is lambda naught here, and if you see clearly, obviously the option C is your best choice. Okay, over to next question. Here we have an electron again, and remember we have an electron again. An electron is accelerated from rest through a potential difference of V volt. So here we have to use that specific formula for electron. And de Broglie wavelength is given. They are asking what is the potential difference. Okay. So remember this. The de Broglie wavelength is equal to square root of 150 divided by voltage in volts. But de Broglie wavelength here is in angstrom. So we have de Broglie wavelength as 1.227 times 10 to the power minus 2 nanometer. So if you convert this in angstrom, you will have it multiplied by 10, and this becomes in angstrom, and make it equal to a square root of this, root of 150 by V. Okay. This actually if you square on both sides, actually, if you multiply 10 by here, actually 12.27. If you square 12.27, you get nearly 150. So 12.27 square becomes 150 times 10 to the power minus 4, obviously, and equals to 150 divided by V. So if you cancel this, obviously V equals 10 to the power 4. Okay, V equals 10 to the power 4 volts. So obviously A is your perfect choice. Next one. So now they say the de Broglie wavelength of a proton and alpha particle are equal. If de Broglie wavelength of a proton and alpha particle are equal, what is the ratio of their velocities? See, as velocity comes in momentum, we can use formula that involves momentum, right? And the de Broglie wavelength of proton is given by h divided by mass of proton. I think you remember, if mass of proton is m, mass of alpha particle is nearly 4m. Okay, so mass of proton is m, velocity of proton is vp, equals h divided by mass of alpha particle is 4m and velocity of alpha particle is, say, v alpha, right? Then we have to actually find vp by v alpha, and if you solve vp by v alpha here, obviously vp by v alpha is 4. So 4 divided by 1 is your perfect choice. It's very simple. If you understand this, believe me, this is going to give you free marks, right? Free marks. Next, a particle moving with kinetic energy E has de Broglie wavelength lambda. Okay, remember, let's relate these two. As you know, if a particle has energy E, the de Broglie wavelength is given by lambda equals h divided by the square root of 2m and energy, which is E. Okay, now they are saying if energy delta E is added to the particle, the wavelength, the new de Broglie wavelength becomes lambda by 2. So what is delta E? So let's manipulate this. Lambda by 2 equals h divided by a square root of 2m and E plus delta E. Let us just divide these two, and if you divide these two, you have 2 on the left. Let's square also, and if you square, you have 4 on the left, and on the right you have E plus delta E divided by E. Okay, and E plus delta E divided by E, if it is 4, solve this and you will have delta E equals 3 times of E. So B is your perfect choice. Next question. Here we have next question. Here in this question, they say a particle is moving 5 times fast as an electron. So if we have a particle which is moving with 5 times velocity than an electron, the ratio of de Broglie wavelength of particle to that of electron is this. We have given the ratio of de Broglie wavelength. The mass of the particle is close to. Okay, the mass of the particle is close to. Okay, let us write the de Broglie wavelength for the particle. So de Broglie wavelength for the particle is lambda p, and lambda p equals h divided by mass of particle times velocity. So let us assume the electron is moving with velocity v. So therefore, according to this condition, the particle's velocity would be 5v. So the particle velocity would be 5 times v, and lambda electron is going to be h divided by mass of electron. Everybody knows mass of electron, and times v. Let us now divide these two equations, and we have lambda p by lambda e, and this ratio is given as this. Okay, so we have 1.9. Let's take an approximation. This values are almost 9, 1.9 times 10 to the power minus 4, and on the right hand side you have mass of electron divided by 5 times mass of particle. Just calculate mass of particle. So mass of particle equals mass of electron times, no, mass of electron divided by 5 times 1.9 times 10 to the power minus 4, and solve it clearly, and you will see the answer is going to be this. You can even check by order. Its order is nearly 10 to the power minus 27, and you can clearly see its order is also almost 10 to the power minus 27. So by just doing some approximation also, you can find the result. Let us see what we have next. So here in this question, they say an electron of mass m and a photon, light photon, have same energy. If they have same energy and the energy is in the range of few electron volts, what is the ratio of de Broglie wavelength of electron and the wavelength of photon? So let us discuss this problem. As photon's energy is given by E equals Sc by lambda, that is the formula for energy of photon, and the de Broglie wavelength of electron is given by h divided by square root of twice times mass of electron and times energy. As you can see, the energy of photon and energy of electron are same, and now they are asking us what is the ratio of the de Broglie wavelength of electron to wavelength of photon. So obviously let us divide these two, and if we divide these two, lambda d divided by lambda is going to be, what is lambda d? Let us write lambda d as h divided by square root of 2 m e, and 1 by lambda. Obviously, can you see 1 by lambda is e upon hc. So 1 by lambda is e divided by h times c. So cancel this h, and if you cancel this h, you can easily see that the ratio is going to be root e by root 2m and 1 upon c. So clearly your D is the perfect choice. Okay, let's move for the next concept, which is electron emission. Electron emission. The electron emission means simply the ejection or emission of electrons from obviously the metal surface. It is the ejection of free electrons actually which move freely inside the volume of metals. Okay, so emission of actually the free electrons from the metallic surface is defined as electron emission. Let me write free electrons. And there are three ways, there are three methods in which electrons are emitted from a metal surface. The first is thermionic emission. Obviously, what electrons require, if they have to come out of metal surface, they require energy. So if you give them heat, they gain energy, and if they gain energy by heat, the emission of electron is called thermionic emission. If you apply a strong electric field near metal, there is electrostatic induction of charges on the surface of metal, and because of this electrostatic pull also, electrons may get ejected from the metal surface, and this is called field emission. And the third, which we are going to discuss in detail, this one, it is photoelectric emission. Here is the photo word. The photo word stands for light. The electric, it stands for the electron, and emission is for emission of electron. So actually, when light falls on some metal surface, and by the projection or by the incidence of light, if electrons are being emitted from the metal surface, means electrons are gaining energy from the light, then this kind of emission is called photoelectric emission. And that is a very great chapter, but that is a very great discovery by Einstein. Einstein got Nobel Prize for the discovery, for the in fact conclusions he made in photoelectric effect. Let us study the photoelectric effect now. So basically we are going to study photoelectric effect now, and the first thing that is that comes in photoelectric effect is the work function. Okay, what is work function? Work function is actually the certain minimum energy, the certain minimum amount of energy that an electron which is inside the metal surface, requires to come out of it. Okay, so if an electron requires a certain minimum energy to come out of the surface, that minimum energy is called work function, and it is the symbol for work function is phi. Okay, we express the work function in electron volts, and usually the work function of metals is between 2 to 5 electron volts. So always remember this, work function is actually the minimum energy that electrons near the surface requires to come out of it. Okay. The second concept is of threshold energy. What is threshold energy? Threshold energy is actually the minimum energy of photon. The minimum energy of photon that makes electron emission from metal surface possible. Okay. So actually, if you imagine a situation that here we have a metal surface and light is being incident on it. Right, light is being incident on it. We can represent threshold energy by symbol ETH. Okay, ETH. If light is being incident on it, right? If say 5 electron volt is the work function of this metal, then obviously the minimum energy of photons, the threshold energy for photons should be at least 5 electron volt, then only they can make some electron to come out of this metal surface. So if energy of photon is more than or equal to 5 electron volt, then only we see some photoelectrons coming out of it. So if the photons have just 5 electron volt, we say the photons have exactly threshold energy. Okay, so actually the threshold energy, this logic explains the threshold energy and the work function are obviously two different phenomena, are obviously the two different properties. One property, the threshold energy belongs to photon, the work function belongs to the metal, but numerically they are same. It is just like suppose for a pen, say the price of the pen is 5 rupees. So 5 rupees is the property of that pen. And if you have to buy that pen, you have to have 5 rupees at least. So this is the property of yourself. This is threshold energy, but they are numerically equal. So always remember the threshold energy and work function are numerically equal. Okay, are numerically equal. Next we see the threshold frequency and threshold wavelength. Okay, if a photon has exactly energy equal to threshold energy, if a photon has energy equal to threshold energy, then the corresponding frequency and wavelength of electron will be called as threshold frequency or threshold wavelength. So if we have ETH as ETH, then ETH equals h nu, as energy of photon is h nu. So the corresponding frequency corresponding to threshold energy is called threshold frequency, and the corresponding wavelength is called threshold wavelength. So as this threshold energy is numerically equal to work function, you can also relate the threshold frequency and threshold wavelength to work function. So as threshold energy is minimum energy of photon to make photoelectric effect, so threshold frequency is the minimum frequency below which photoelectric effect would not happen, and because of the inverse proportionality we can say the threshold wavelength is the maximum wavelength above which the photoelectric effect does not happen. So photoelectric effect occurs, photoelectric effect occurs if frequency of photon is more than threshold frequency and wavelength of photon is less than threshold wavelength. That's simple. Always remember this point. Let us now understand how this experiment is performed experimentally, and it is done under very special circumstances. Okay, so let me show you the experimental setup for photoelectric effect. Here we have a tube. Can you see the tube? And this tube is evacuated. Evacuated means all the air inside it is withdrawn so that there is no air inside it, so that the electrons or any particle can move freely without any hindrance. Okay. Yes, the voltage across these two electrodes is actually set initially to be 0, and this is called cathode and this is called anode. Okay, so these two electrodes are made of metals. This is actually electron emitter and this is actually electron grabber. Okay, this is the torch from where we send light on this cathode, and when we send light, the electrons come out of the cathode and they move inside this medium. Okay, so we have two parameters. As you know, the intensity, the light intensity depends upon the number of photons coming and also on the frequency. So suppose we increase intensity, suppose we put some light on it, and as we put some light on it, can you see the light falls on cathode, and when light falls on cathode, some electrons are being emitted. Electrons are being emitted. Okay, can you see few electrons are faster and few electrons are slow, but anyway, if electrons are being emitted and if they are moving, they will move in this region and they all will reach anode, because the potential difference across this is 0. There is no electric field between the two electrodes, so electrons neither they will accelerate nor they will retard. So they will move with constant speed, the speed with which they are emitted, and they move like this. Few are moving faster, few are moving slower, because experimentally we see all electrons are not emitted at same speed. So now we will understand a very crucial idea of this experiment. And what is that? Suppose we keep the intensity of light constant, means we keep the number of photons falling on the cathode constant by keeping the intensity constant, and we increase the wavelength, or you can say we decrease the frequency. So suppose we increase the wavelength. This time the wavelength is approximately 400 nanometer and lots of electrons are being emitted. Okay, if we increase the wavelength, by increasing the wavelength, by increasing the wavelength, the energy of photons falling on cathode decreases, and if energy of photons decreases, then you can see now the electrons are being emitted with a little lesser energy. You can see that the electrons are moving slower than earlier. And if you further increase the wavelength, means further decrease frequency, very few electrons come from cathode and with obviously very low energy. And if we keep on increasing the wavelength, let's say around 550 nanometer, you can see the emission of electron has stopped. This was the idea that forced people to believe that light has particle nature, because if we believe in wave nature, energy is still falling, and if we wait, a lot of energy can fall on cathode, but it's still no electrons are being emitted. Okay, so that explains the interaction between photon and electron is particle like. Okay, by particle like we mean that a photon collides with electron, gives it energy, like particle gives energy to other particle in collision, and then by gaining that energy, electron pops out. If the light would have only wave nature, then by waiting for sufficient time, electron should have come out whatever be the frequency of light, because energy is unlimited here. Okay, so that was the idea. Let us now understand the same idea, okay, and the mechanism of photoelectric effect, right? Okay, suppose we have a metal plate like we had in the experiment as cathode, and the light is falling on it. Okay, say the frequency of light photon is nu, so energy of each photon is going to be h nu. When these photons enter metal, the free electrons inside metal first absorb this energy. Okay, so electrons gain energy equal to h nu. But now when they try to come out, okay, they have to spend a little energy equal to work function of metal so that they can cross the attraction potential or the field of metal surface, and when they come out they lose energy equal to work function, and the remaining energy is converted into kinetic energy of electron. This idea explains that if the energy of each photon is same, the work function of metal is obviously same, so each electron must come out with same energy. But what happens? You have seen in the experiment that few electrons are fast and few electrons are slow. So electrons come out of the metal with a big range of energy, not just a single constant energy. Few are very slow, few are so slow that they barely move. So how this happens? Let us understand in detail. Okay. When electrons gain this energy h nu, they try to come out of the metal surface, and before they come out of the metal surface, they sometimes collide with other electrons and ions of the metal. And in these collisions, they may lose some more energy in this gained energy h nu. And if they lose more energy during collisions, obviously the electrons coming out would have less energy. Only the few electrons who come out the metal surface without colliding with any other particle have this energy equal to h nu minus 5. So we can say only few electrons come with this maximum energy, and the remaining electron, since they lose some energy with during collisions, okay, they come out with energy less than this. So this is actually the maximum kinetic energy of, in fact, fastest electron. So this is kinetic energy of electron maximum. As we have no science, no clue that how much energy electrons will lose during collisions, so we cannot calculate the energy of each electron, but only we can calculate the kinetic energy of maximum energetic electron. So that is the limitation of this equation. You can also write h nu minus phi equals to kinetic energy of particle mass electron can be written as half m v max square. And remember, by using this formula you can calculate speed of the fastest electron only. Okay, and all other electrons will have kinetic energy between 0 and this maximum, and they will have a speed between 0 and this maximum. So you can say the kinetic energy of electron is between 0 to kinetic energy of electron maximum obtained by this formula, and even the speed of electron is between 0 to V maximum obtained by this formula. So that is the Einstein's energy equation. Okay, that is the Einstein's energy equation, which gives us a relationship between kinetic energy of maximum energetic electron and frequency of light photons. Okay, let us review it again. So we have kinetic energy equals kinetic energy of electron equals h nu minus phi, which is work function. H nu can also be written as Sc by lambda, and work function can be written as Sc by threshold wavelength, as you already know, and K can be written as half mv square if required. Okay, so if we plot a graph between kinetic energy of electron and frequency of light photon, you can see this is a y equals to mx minus c type of graph. It has positive slope, okay, and it has negative y-intercept, So obviously the graph would look like something this. Okay, so this is the graph between maximum kinetic energy of electron versus frequency. It's a linear curve, you can all see. If we choose two different metals or three different metals or any number of metals, remember the slope of this equation is h, and which is a universal constant. So slope of every curve is constant, and that is why for each metal we will get parallel curves. So remember, the slope is equal to h, as you can see from the formula. Okay, so slope of each curve would be same, and obviously the work function is different, and if work function is different for different metals, the y-intercept would be different for different metals. Bigger the y-intercept means bigger is the work function, right? I think you understand this formula. Okay, this graph. Obviously, this represents the threshold frequency. This represents the critical frequency or threshold frequency. If frequency is more than the threshold frequency, say for metal 1, the threshold frequency is Fc1, and if frequency is more than this, you get photoelectrons, and we get kinetic energy of photoelectrons. Below this frequency, there is no photoelectron, so we have shown this by a dotted line. It means no energy is available, but this is actually the work function of metal 1, and similarly this is the work function of metal 2. So this is about the graph between kinetic energy of fastest electron and the frequency of photons. Let us now solve few problems based on this concept. So in this question they say the light of frequency 2 nu naught, where the threshold frequency is only nu naught, okay, is incident on a metal plate, and the maximum velocity of electron emitted is v1. Okay, so we can write Einstein's equation as energy of photon is 2h nu naught, because frequency of photon is 2 nu naught, and work function is going to be h nu naught because threshold frequency is only nu naught, and this equals half m v1 squared. Simple. In the next line they say the frequency of incident radiation is increased to 5 nu naught, and maximum velocity of the electrons emitted from the plate is v2. So what is v1 by v2? We have to find the ratio v1 and v2. So according to the next condition, we can say 5h nu naught minus the same work function, because metal is same here. We can write h nu naught as the work function of metal equals to half m v2 square. Okay, and if you divide these two, you will have 1 divided by 4 on the left. It's easy to calculate, and on the right you have v1 squared by v2 square. So obviously v1 by v2 is 1 by 2, and D is your correct choice. Let us move for the next question. Here they say the light of frequency 1.5 times of the threshold frequency is incident on a photosensitive material. Okay, what will be the photoelectric current if frequency is halved and the intensity is doubled? Okay, If you double the intensity, obviously the number of photons being incident are going to multiply. Definitely they are going to multiply. But see, what are you doing exactly to frequency? You are reducing the frequency to half. So if it is initially 1.5 times of threshold frequency, the new frequency would be 0.75 times of threshold frequency. So the new frequency is less than the threshold frequency, and if frequency is less than threshold frequency, no photoelectron will be emitted, and if there is no photoelectron emitted, though no electron emitted, the current associated with photoelectron will be definitely zero. So A is your perfect choice. Next question. Here we have electromagnetic wave of wavelength lambda. So we have photons of wavelength lambda, and they're incident on a photosensitive surface, negligible work function. You can ignore the work function in the calculations. Mass of the photoelectron is m, and they are asking us what is the Broglie wavelength of photoelectron. Okay, so let us apply again the Einstein's equation of photoelectric effect. It says the energy of photon is actually Sc by lambda. Sc by lambda minus work function is actually the kinetic energy of fastest electron. So we can write it as K max. But as the work function is negligible, we can ignore it and take its value to be almost zero. So this is kinetic energy. And if we know the kinetic energy, de Broglie wavelength, the de Broglie wavelength, which is lambda d here, can be written as h divided by the magnitude of momentum, which is equal to a square root of 2 m and kinetic energy. And can you see the kinetic energy equals Sc by lambda? So we can write h c by lambda. So square root of lambda goes in the numerator, and this is de Broglie wavelength. And if you you manipulate this and check the answers, you will find the correct relation is C. So C is your perfect choice. Okay, so let us see what we have next. Here we have a surface of certain metal, and it is illuminated with a light of wavelength lambda 1, which is 350 nanometer. Okay, and then by light of wavelength 540 nanometer. So initially we make this incidents with lesser wavelength of light, and then by higher wavelength of light. It is found that the maximum speed of photoelectron in the two cases differ by a factor of 2. Obviously, in initial case when we have less wavelength, we have higher energy of photons. So in that case, the speed can be assumed, the speed of maximum energetic electron can be assumed to be 2v, but in the next case it would be v, because the ratio is 2. So let me write the Einstein's equation twice. So initially we have, according to first condition, we have Sc by lambda 1 minus work function, and it is equal to half m. We can assume the speed in the first case to be 2v and then the second case to be v, because the ratio is 2. So half m 2v whole square, and the next case we have Sc by lambda 1 lambda 2 minus phi equals half m v square, right? If you divide these two, it's very easy. You know Sc as 1240 electron volt nanometer. So you put lambda in nanometer and you will have this value. Okay, here the ratio would be 4, and you can easily calculate the work function, and after solving these two equations, after dividing these two equations, only you will see the phi will be unknown. So after solving, you will see the work function phi is close to 1.8 electron volt. So obviously option D is your correct choice. Okay, so let us see what we have next. Next question. In next question, they say a metal plate whose area is 10 to the power minus 4 meter square. It is illuminated by radiation of intensity this 16 milliwatt per meter square. The work function of the metal is 5 electron volt. The energy of incident photon is 10 electron volt, and only 10% of the photons, 10% of the photons produce photoelectrons. They are asking us finally, what is number of emitted photoelectrons per second and their maximum energy. Okay. As you know, the energy of photon is 10 electron volt and work function is 5 electron volt. By using Einstein's energy equation, you can easily write the energy of photon 10 minus work function 5, and this is kinetic energy of maximum energetic electron. So maximum energetic electron's energy is 5 electron volt obviously, and you can see we can simply ignore option D, but in all three we have 5 electron volt. Okay, so we will have to calculate the number of photoelectrons emitted per second. Okay, so let us proceed. We have intensity as 16 milliwatt per meter square. So as 16 milliwatt, so by milli we can write 10 to the power minus 3. So it becomes 16 watt, and it is the power falling per unit area. So if we multiply this by area, which is 10 to the power minus 4, this is the exact power or energy falling per second on that surface. As it is the energy falling per second, if we divide this by the energy of photon, the energy of each photon, which is 10 electron volt, okay, which is 10 electron volt, right, we will get the number of photons falling per second. So let us divide it by 10. We will have to convert this into joules, so 10 times 1.6 times 10 to the power minus 19, and this is the number of photons falling per second. Okay, and as only 10% photons result into photoelectrons, so number of photoelectrons emitted would be 10 by 100. Okay, so let us calculate this. This is 16, this is 16 cancelled out. After solving this, you see this value is equal to 10 to the power 11, and if it is 10 to the power 11, the A is your perfect choice. Okay, so over to next question now. Okay, here we see the radiations of wavelength 6561 angstrom fall on a metal surface to produce photoelectrons. Okay, so as we have wavelength, the energy of photon is going to be Sc by lambda, and as Sc is 12,400 electron volt angstrom divided by 6561, this energy is very close to 1.9 electron volt. Okay, so this is energy of photons, and when these photons are incident, the photoelectrons are being emitted, and those photoelectrons, not all, only the fastest photoelectron when enter a magnetic field of 3 times 10 to the power 4 minus 4 Tesla, they make a radius of 10 millimeter. So as we know, the radius of electron would be momentum by QB, or momentum can be written as square root of 2m k by QB. Here I can write R as 10 mm, the magnetic field as this much Tesla, the charge of electron you already know, it is 1.6 times 10 to the power minus 19. The mass of electron is known to everyone. So put all these values here and you will find the kinetic energy of fastest electron is 0.8 electron volt. Okay, so it is 0.8 electron volt. Now you know energy of photon minus work function equals to the kinetic energy of fastest electron. So we have E as 1.9, K max as 0.8. So phi becomes 1.9 minus 0.8, which is 1.1 electron volt. So work function of this metal is 1.1 electron volt, and this is your correct choice. Next, we have to study what is stopping potential. And to understand this stopping potential, let us move to the same experiment again. Okay. So let us decrease the wavelength or increase the frequency. Now, photoelectrons are being emitted. Lots of photoelectrons are being emitted. And the potential difference across the electrode is 0. Okay. Suppose we make the potential of anode to be negative as compared to cathode by using this battery. Let us see what happens. Okay. Can you see few electrons which are fast enough? Okay, let me keep it minus, but not this much minus. Let's keep this as, yes, the voltage now is 0.6 volt. So voltage here at anode is 0.6 volt negative as compared to cathode. Okay. So now you see few electrons which are fast enough, they are moving towards right and they are reaching anode, but electrons which are slow, they are repelled by the negative potential of anode, and they come to some point and they return back to cathode. Okay. But the electrons which are fast, which have more kinetic energy, they are able to reach anode. Suppose we decrease potential by some more value. Let's now potential is 0.8 yes volt. Still few electrons are reaching anode and the remaining are going back towards cathode. If we further increase the negative potential of anode, you can see no electrons are reaching, only few are just reaching to the point, to this value, and they are returning back. So no electron is going to make to anode. Okay. This voltage is called actually the stopping potential, because it is stopping even the fastest electron to reach anode. Okay. So remember this point. When even the fastest photoelectron just fail to reach anode, this negative potential of anode is called stopping potential. Okay. And obviously it is equal to, say, the kinetic energy of fastest electron is Ke max, and the energy they are going to lose in the path is E times the negative voltage, the magnitude of negative voltage in the path. And if these two are equal, even the fastest electron will just reach very close to anode, but it will not touch anode and will come back to cathode. And this is called stopping potential Vs. So you can see stopping potential is actually proportional to Ke max. Okay. As we know the equation of Ke max, so stopping potential's equation can be written as V stopping equals Sc by lambda or h nu divided by E minus work function divided by E. And you can again see the stopping potential versus 1 over lambda is a straight line curve, or if you replace Sc by lambda by h nu upon E, you can see the stopping potential versus frequency is again a straight line curve as shown in the figure. But here the slope is h by E. But both h by E is a universal constant. H upon E is a universal constant. Therefore, you take any metal of the world, draw their separate stopping potential versus frequency curve, and you will see all the graph would be parallel to each other, because slope for all is a universal constant equal to h by E. Obviously, at this frequency, we get zero stopping potential. Only after this frequency we get some stopping potential. Means after only this frequency the electrons are being emitted. So this is threshold frequency for metal 1. This is threshold frequency for metal 2. And the slope of this curve is actually h divided by E. So the graph is similar to the graph of kinetic energy versus frequency. The only difference is the slope is h by E, and here we do not get work function, but we get work function divided by charge of electron. So that you have to remember. Okay. Let us solve few questions based on stopping potential. And here we have a certain metallic surface illuminated by monochromatic radiation of wavelength lambda, and the stopping potential is 3V0. Okay, so let's write them in Einstein's equation. So we have energy of photon as Sc by lambda minus the work function can be written as Hc by threshold wavelength, say it is lambda naught. Okay, right, equals to the stopping potential is 3V0. If stopping potential is 3V0, the kinetic energy of maximum energetic electron would be E times 3V0. And as they say next, if the radiation is of wavelength 2 lambda, the stopping potential is only V0, the work function remains the same. So we can write Sc by 2 lambda minus Sc by lambda naught equals E V0. Now you divide these two and solve for lambda naught, and I'm sure you will get lambda naught as 4 times lambda. So correct answer here is 4. Okay, so over to next question. Here we have a beam of electromagnetic radiation whose intensity is 6.4 times 10 to the power minus 5 watt per centimeter square, and it has a wavelength lambda is 310 nanometer. It falls normally on a metal surface of work function 2 electron volt, and whose surface area is only 1 centimeter square, and only 1 in 1000 photons eject photoelectrons. So they are asking us what is number of photoelectrons ejected in 1 second. Okay. Actually, we will first check whether the photoelectrons are really being emitted or not. So let us see what is the energy of photons. So as energy of photon is given by Sc by lambda, Sc is 1240 and divided by the energy of photon as, wavelength of photon as 310, and if you solve this you see the energy is 4 electron. And if energy is 4 electron volt, which is more than the work function of the metal, obviously the photoelectrons would be emitted. Okay. If photoelectrons are emitted, let us see how much. So intensity is 6.4 times 10 to the power minus 5. As this intensity is per centimeter square, you multiply it by the area of plate 1 centimeter square, and this you get energy falling per second. If it is energy falling per second divided by the energy of 1 photon, okay, energy of 1 photon, which is 4 electron volt only. So 4 electron volt multiplied by electronic charge, that is 1.6 times 10 to the power minus 19, it gives you the number of photons falling per second. And if it is number of photons falling per second, only 1 photon out of 1000 gives photoelectron. So if it is number of photons falling per second, 1 divided by 10 to the power 3 would be the number of electrons emitted, the number of photoelectrons emitted per second, or n dot. You solve it and you will find this answer is actually equal to 10 to the power 7. So here the value x is actually equal to 7. Okay. So let's see what we have next. Here we again have photons of energy 4 electron volt strike the surface of a metal A, and ejected photoelectrons have the maximum kinetic energy Ta. Okay, so let's group them in Einstein's equation of photoelectric effect. Okay, So photons of energy 4 electron volt minus work function of metal A, and this equal to the maximum kinetic energy TA. That's your first equation. Okay. And they also say the de Broglie wavelength of photoelectron is lambda A. So you know the lambda A equals h divided by square root of 2m TA. Right, 2m TA, because the de Broglie wavelength is h upon 2m and the energy. Okay, that's first equation. The next condition says the maximum energy, the maximum kinetic energy of photoelectrons liberated from another metal B by photons of energy 4.5 electron volt is TB. Okay, so 4.5 electron volt minus the second work function T phi B equals to TB, and TB is actually TA minus 1.5. So I am writing directly TA minus 1.5. And the new de Broglie wavelength is lambda B, which is twice of lambda A. Remember, it is twice of lambda A. So I can write TB as twice of lambda A, and it is equal to h divided by square root of 2m TB, and TB can be written as TA minus 1.5. That's the equation. If you take a ratio of these two, you will have on the left 1 by 2. Square it, you will have 1 by 4, and equals to, you will have TA minus 1.5 divided by TA on the right hand side. And this gives you TA as 2 electron volt. So here you have TA as 2 electron volt. Remember this point. Okay. They are asking us what is the work function of metal B. Okay. So we have to find work function for metal B. So we will put this 2 electron volt here. It will be 2 minus 1.5, that is 0.5, and work function for metal B would be obviously 4 electron volt, and D is your correct choice. So put this TA here and you have your answer. That's simple. Okay. Now there are few important graphs which are theoretically asked in different examinations. Let us understand them. Okay, you all know when light is incident on metal surface, the photoelectrons are being emitted. Okay, the photoelectrons are being emitted. If you set the potential difference between two electrodes 0, is still the photoelectrons reach from cathode to anode. So let us see this experiment again. Yes, if the potential difference here is 0, let us put it 0. Now the potential difference across these two electrodes is 0. There is no electric field here, and all the electrons which are coming out of the cathode are reaching anode. Only few electrons which come out of the cathode with almost 0 kinetic energy, they form a little cloud here. But remaining all electrons which have some speed, they reach anode. When they reach anode, they have this closed path back to cathode. So by this path they come back to cathode. So there is no deficiency of electron here and extra electrons here. They come back, and as the process is on, the electrons move like this, and a current flows in anti-clockwise direction, and that current is shown here. So this is called photocurrent. The photocurrent is a current associated with photoelectrons. Okay. So remember this point, if the potential here is 0, there is some photocurrent if the circuit is on. But if you make this potential a little positive, this time this potential of anode is positive, and because this is positive, this is negative, this positive potential attracts photoelectrons. You can see the speed of photoelectrons is increasing as they are moving towards anode. They are getting faster, and even the electrons which make a cloud here, which have zero kinetic energy, they too gain some energy and they too reach anode. So by those electrons which were forming a cloud here, this time even those electrons too are reaching anode. So the photocurrent increases a little when you make it positive, but if you make it further positive, there is no change in current. There is no change in current because all electrons are reaching anode. And if all electrons are reaching anode, now the current cannot increase because the number of electrons being emitted are fixed. They are fixed by the light falling on cathode. Okay. So you see this point. If you make the anode a little positive, the current increases a little and then it becomes flat, because if you increase potential further, as all electrons are reaching anode, so current cannot increase. But what happens if you decrease the potential? You decrease the potential of anode, you make the potential of anode negative as compared to cathode. Here what happens? Yes. Now you see a lot of slow electrons are not reaching anode, and therefore the photocurrent must decrease because electrons reaching this anode are decreasing. So electrons circulating in this circuit are decreasing, so current must decrease. And if you further increase the negative voltage of anode, what happens? At some value of voltage, even the fastest electron do not reach anode and they all go back. Obviously the flow of electron has stopped, the circular flow of the complete circular flow of the electron has stopped and the current is stopped. So let us understand this in the graph. If we try to plot the photocurrent versus anode potential and we keep the anode potential 0, still we get some current. Can you see? It is the current at 0 volt. But if we increase the voltage, if we increase the anode voltage, we make it positive, the photocurrent increases a little and then it becomes constant, because if you further increase the voltage, there are no extra electrons, all electrons are reaching anode, so the number of electrons flowing per second is constant, so photocurrent is constant. Now if you decrease the anode voltage or you make it negative, the photocurrent decreases very sharply, because as you making it negative, the negative potential of anode is actually repelling electrons to go back to a cathode. So the electrons are decreasing, the circulating electrons are decreasing, and at stopping potential, we already know the stopping potential, at a stopping potential the whole current stops. So current stops at the stopping potential, and this is the graph of photocurrent versus anode potential. We can compare three graphs of photocurrent versus anode potential and let us understand closely what is the difference between these three graphs. Okay. If we compare between 1 and 2, let us 1 and 2. You can see the stopping potential for 1 and 2, Vs1 and Vs2 are same. As stopping potential depends upon the frequency of incident radiation, obviously the frequency of incident radiation for 1 and for 2 are same. So nu 1 equals nu 2. I am assuming all the radiations are falling on the same metal surface. We have same work function, suppose. So nu 1 is equal to nu 2. But how the photocurrent, the saturation current is more in graph 2? The reason is obvious. The more electrons are being emitted here, and that's only possible if more number of photons are falling in graph 2. So if the n1 dot is the number of photons falling in case of graph 1 and n2 dot is the number of photons falling per second in case of graph 2, or let's say intensity of light I1 and I2. So if I1 is more than I2 because frequency is same but number of photons of 2 are large, or you can say n1 dot, actually this is I2, I must say, yes, I2 is large and n1 dot is less than n2 dot, as can clearly be seen from the graph. Because saturation current is more and current is more means more electrons are coming, and more electrons are coming because more photons are being incident, right? So that's the relation between 1 and 2. Now if we compare between 2 and 3, if we compare between 2 and 3, obviously they have same photocurrent, and if they have same photocurrent, same saturation current, means equal electrons are being emitted. And if equal electrons are being emitted in both case, it means the photons falling per second are same. So for 2 and 3, the photons falling per second are same. If same number of photons fall per second, same number of electrons will be ejected. But as stopping potential is different. The stopping potential for 3 is more negative, means the photoelectrons emitted in case 3 were more energetic. That is why we had to use bigger negative potential for graph 3. So here we have more energetic photoelectrons, and if we have more energetic photoelectron, it means for graph 3 we have more energetic incident photons. So for 3 we have bigger frequency than 2. Okay. And if you compare between 1 and 3, obviously these are obvious. Between 1 and 3 again we have frequency of 2 and 3 equal, so V3 is more than V1, it's obvious. And as N1 dot is less than N2 dot, so we can again say N1 dot like this. So this is the complete relation between the three, I must say the three graphs. Okay, let us move for the next graph. Next we have photocurrent versus intensity. Okay, let us understand what is intensity. As intensity of incident radiation is actually N dot h nu by area of cross section of beam. N dot is actually the number of photons coming in 1 second. H nu is energy of one photon or average energy of one photon, and area is the cross section area of the beam. This is the intensity, and you know the intensity depends on both N dot and nu. So suppose I am keeping the frequency constant, we can say the intensity is only proportional to N dot if we keep the frequency constant frequency. And for increasing intensity, we will have to increase N dot. Okay, so we increase N dot, and as number of electrons, if we assume number of electrons coming out of metal surface by N dot, the N dot is the number of photons, photoelectrons coming out of the metal surface per second. This is actually experimentally seen to be proportional to capital N dot. These are, remember, the number of photoelectrons emitted per second. These are the number of photons incident per second. So we see these two are proportional to each other. Okay, and if these two are proportional to each other, these are the number of photoelectrons. So N dot E becomes the photocurrent. So now you see IP is proportional to N dot and N dot is proportional to N. So you can say the photocurrent is proportional to N dot, and which in turn is proportional to intensity. So IP, if frequency is constant, and obviously the frequency is more than threshold frequency, obviously threshold frequency is lambda th, and frequency is more than threshold frequency, then we see the photocurrent is proportional to intensity, and you increase the intensity, photocurrent increases, right? So that is why in the last graph I said between 1 and 2, the intensity of 2 is more than intensity of 1, because as you increase intensity, the photocurrent increases. Okay, so that was all about the graphs in photoelectric effect. We have solved many examples in it, and now it is time to understand atomic structure. I hope you already know there are many elements in an atom. There are protons, there are neutrons, there are electrons. And how these are arranged in an atom, how they are placed, what is their motion, whether they are at rest or they are vibrating or they are oscillating or they are circulating. Study of all these things is called atomic structure. Initially, there were many models to understand atomic structure, but the most famous and most promising model was of Niels Bohr's. So, Niels Bohr models was only applicable to those species or those atoms which have only one electron in them, like hydrogen atom, He plus ion, lithium plus ion, and these all have one electron. So remember this point, Bohr's model is only valid for single electron atoms or species, like we say them hydrogen like atoms because they all have single electron. Okay, and this model can also explain the spectrum of these atoms. Okay, so let us now understand what are the main postulates of Bohr's model. There were two actually. Bohr said every electron or the one electron which revolves around nucleus in circular orbit, just like Rutherford's, and the required centripetal force comes from the electrostatic attraction between the nucleus and the electron. So what he said, the required centripetal force, that is m v squared divided by r is the radius, okay, and this comes from the electrostatic attraction. What is electrostatic attraction? 1 by 4 pi epsilon naught charge of nucleus times charge of electron. So charge of nucleus is z times e and charge of electron divided by r square. You can cancel one r from here, and that is equation number 1. This is the first equation of Bohr. Okay, and the second and very important postulate was, he said only those orbits in which angular momentum of electron is integral multiple of h upon 2 pi, electron can be stable in only those orbits in which its angular momentum is integral multiple of h upon 2 pi. If electron is orbiting in these spatial orbits, we say electron is in stationary orbits, and we believe in these orbits electron will not emit energy and energy of electron will remain conserved. So only these stable orbits, these stationary orbits are possible for stable orbiting of electron. So according to this second Niels Bohr's postulates, he said the angular momentum L of electron is actually equal to m times v times r, and it should be integral multiple of, means n times of h divided by 2 pi, where h is Planck's constant, and n can take values 1, 2, 3, 4. So remember, n here is principal quantum number, or you can say it represents the number of orbit. It means if n is 1, it is the first orbit or ground state. If n is 2, we call it a second orbit. Okay, so these are the two main equations. You can call this as equation number 2. And if you see, the only variables here are v and r. See, v and r are the only two variables. If you believe only one equation is correct, every possible value of v will be possible. But as we have two equations in v and r, not all values of v, not all values of radii are possible. Only certain radii would be possible. Only certain velocities on those radii will be possible. So if we solve these two equations, remember, if we solve these two equations, we get few results. We get certain results. Let us see them and try to remember them. Okay. So these are the results. After Bohr's postulates, after Bohr's we derive parameters. If we solve these two equations, okay, radius. So radius of nth orbit, remember, radius of nth orbit is equal to r naught n square by z, where n is principal quantum number and z is atomic number. Okay, r naught is actually equal to 0.53 angstrom. So always remember, this is the radius of nth orbit of hydrogen-like atom. Okay, never forget this. Velocity. Velocity is equal to v naught z by n, and the velocity v naught is actually c upon 137, where c is the speed of light. So in hydrogen-like atom of atomic number z, the nth orbit will have a electron's velocity given by this equation. Okay. So if you want to find time period, that's simple. If you know radius and velocity, everything else is simple. Time period. Time period is simply 2 pi r by v. 2 pi r by v. So this is actually Rn, means like this. So if we are talking about electron's time period in nth orbit, okay, in nth orbit, the time period would be 2 pi Rn by Vn, where Rn and Vn are the radii and velocity in nth orbit. Okay, and remember one point, the time period, this time period is proportional to actually n cube by z square, n cube by z squared. Okay, then frequency, as frequency is 1 by Tn, 1 by time period, so automatically it becomes proportional to z square by n cube. If we talk about the kinetic energy of electron, the kinetic energy of electron is simply given by half mv square. So in nth orbit we have half mvn square, and as we know velocity, see, as velocity is proportional to z by n, obviously the kinetic energy should be proportional to z square by n square, and the remaining constants, if clubbed, we have the value 13.6, and this is an electron volt, remember. So this is a very important point. The kinetic energy of electron in nth orbit is 13.6 z square by n square, where n is principal quantum number and z is atomic number. Let's proceed. Okay, so we know the kinetic energy. If we want to know the potential energy of electron, obviously potential energy is given by k q1 q2 by r. Okay, k is, you know k, what is k? K is 1 upon 4 pi epsilon naught. q1 q2 is ze square divided by r, and as one electron is positive, nucleus is positive, electron is negative, we have negative potential energy. Okay, and after solving this, okay, you see that potential energy is equal to actually twice of kinetic energy but negative. So always remember, in circular orbit, if electron is revolving in circular orbit, the potential energy is equal to negative of twice of kinetic energy. Remember, this is a very important or very helpful relation. And if we want to know the energy of electron, that is total energy of electron. So total energy is always potential energy plus kinetic energy, and potential energy plus kinetic energy, if you add them, so I think you can see here u plus k is equal to minus k. So it is equal to negative of kinetic energy. So always remember, the total energy equals to negative of kinetic energy. So these are the few initial formula you should remember. Let us solve few questions based on these. Okay. So here we have a question where they are asking us the ratio of kinetic energy to the total energy, of an electron in Bohr orbit of hydrogen atom. Okay, we just understood that the total energy E equals to minus times of K. So the ratio of total energy to the ratio of kinetic energy to the total energy is simply K divided by minus K, that is 1 upon minus 1. So obviously the B is your correct choice. Next question. Now they say the total energy of electron in an atom is 3.4 minus 3.4 electron volt. So if total energy is minus 3.4 electron volt, remember, its kinetic and potential energies are, let us see what are kinetic and potential energies. As you know, the total energy is equal to negative of kinetic energy. By this formula, the kinetic energy would be 3.4 electron volt. And as potential energy is minus of 2k, so potential energy automatically becomes minus twice of 3.4, that is 6.8 electron volt. So we have kinetic energy 3.4 electron volt and potential energy minus 6.8 electron volt, and the correct option is obviously C. Okay, over to next question. Now they say, what is the de Broglie wavelength of electron in third orbit of He plus ion? Okay, in third orbit. So remember, in third orbit, the radius of third orbit would be R naught. If we have an He plus ion, remember, if we have an He plus ion, the radius would be R naught n square by Z. Okay, the third orbit means n is 3 and Z is 2 because for He atomic number is 2. So we have R naught times 3 square, that is 9 divided by 2. So this is the radius, right? And as we are in third orbit, the angular momentum means MVR, the angular momentum MVR equals, the MVR equals N H upon 2 pi, right? NH upon 2 pi, remember this. So if we bring this 2 pi here, 2 pi R3, let's say R3 because we are in third orbit, divided by n is 3, and this equals H divided by mv. And I think you already know H upon mv is the de Broglie wavelength. So this is 2 pi R3 divided by 3. Put R3 as this and solve yourself and you will get the de Broglie wavelength to be approximately 4.9 angstrom. So the best option is 5 angstrom and D is your correct choice. Okay, next. Let us see what we have next. They said now energy of electron in second orbit of He plus ion. Okay, so what is energy? As we already know, the energy of electron is given by minus 13.6 because it is equal to negative of kinetic energy, minus 13.6 Z square by n square. Okay, let us see what is Z, the atomic number. As we are talking about helium, the atomic number is 2, and as we are talking about second orbit, n is also 2. So 2 square by 2 square cancels out and energy is simply minus 13.6. So B is your correct choice. Okay, next. Here they say the electron makes a transition from an excited state to the ground state, means the electron is coming from a higher state to the ground state. What is ground state? The first orbit is your ground state. Okay, so electron is jumping from a higher state to lower state. What happens to the energy? Okay, let us see. As you know, all energies are proportional to 1 over n square. So as n is decreasing, the magnitude of energy should increase, right? The magnitude of energy should increase, but only kinetic energy is positive. That says kinetic energy must increase, and potential energy and the total energy, they both are negative, so they are actually decreasing. So kinetic energy must increase and potential energy, total energy must decrease. So kinetic energy increases, but potential energy, total energy decreases. So C is your perfect choice. Let us see what we have next. Here they say, in this question they say, some energy levels of molecules are shown in the figure. The ratio of the wavelength R, lambda 1 by lambda 2 is given by, okay, let us see. As you know, the difference of these two energies is simply E by 3. I think you all can see the difference is E by 3, and this E by 3 is equivalent to a wavelength lambda 2, a wavelength of photon of wavelength lambda 2. So it is equal to Sc by lambda 2, and difference of these two is actually E, and E is equivalent to Sc by lambda 1. So if we divide these two, you get lambda 1. If we divide these two, we get 1 by 3 on the left and lambda 1 by lambda 2 on the right. So lambda 1 by lambda 2 is simply 1 over 3. So A is perfect. Let's move ahead. This time they are asking, what is the time period of revolution of electron in ground state orbit in a hydrogen atom? Okay, so they are saying the time period of revolution of electron in ground state orbit of hydrogen atom is 1.6 times 10 to the power minus 16. Okay, as I just told you, the time period is proportional to n cube by z square. N cube by z square. So T equals to some constant times n cube by z square. So we have time period as 1.6 times 10 to the power minus 16. So 1.6 times 10 to the power minus 16 equals k times, okay, ground state. For ground state we have n equals to 1, and for hydrogen atom we have z equals to 1. So all these are 1. So we can say it is equal to k. That is the first equation. Now they say, what is the frequency of revolution of the electron in the first excited state? What do we mean by first excited state? Actually, the second orbit is called first excited state, because after ground state, every state is excited state, and the second orbit is the first excited state, right? So if we make n equals to 2, so t, but at the place of t we can write 1 over frequency. Yes, because they are asking us frequency, and 1 over frequency equals k times, we have this n equals to 2 now, so 2 square and divided by z square is 1. So let us put the value of k here. So we have frequency equals 1 divided by k, which is 1.6 times 10 to the power minus 16 times 2 cube. It is 2 cube actually, so 8. Okay. Now, if you solve this, you will get approximately 7.8 times 10 to the power 14 hertz. Okay. So obviously, your perfect answer is C, 7.8 times 10 to the power 14. Okay. So now we will study what is absorption and absorption spectra. Suppose we have a container which contains some hydrogen gas in it, right? And we send some electromagnetic waves, means light here, and say these waves contains almost all kinds of photons, okay, from very low energy photons to very high energy photons. Okay, when these photons are passed through this hydrogen gas, some of the photons are being absorbed by the hydrogen atom, and this is called absorption. But only some of the some of the photons are being absorbed, and that is important. Let me explain it. Okay, so just understand, if we send some light through hydrogen gas, some of the photons are absorbed. Okay, so here we get the unabsorbed light, and if the unabsorbed light is passed through a prism, the prism makes a spectrum of it, means every wavelength is splitted into different colors. Every wavelength has a different place at this screen. So what we see here, the photons which were actually absorbed here are missing in this spectrum, and at their place we get some dark lines, and this kind of a spectrum is called absorption spectrum. Listen again, we send some light, some photons are absorbed here, and the photons which are absorbed are missing here in the spectrum, and this spectrum is called absorption spectrum. So what is an absorption spectrum? The whole absorption spectrum is bright, but it has few dark lines corresponding to the photons which were being absorbed by hydrogen atom. Okay. So what happens when light passes through a hydrogen gas? Few electrons are absorbed. Okay. But remember few very important point. Only those photons are absorbed which have energy exactly equal to the ground state energy and any of the excited state energy. So if we see the energies, energy of ground state is 13.6. We are talking about hydrogen atom. Energy of first orbit would be minus 3.4. Energy of third orbit would be minus 1.5. I am finding it using the formula. Energy equals minus 13.6 divided by n square. As z equals to 1, so we can forget about z. We are talking about hydrogen atom. And for hydrogen atom, this is the energy. For ground state, we put n equals to 1 and we get this energy. For this state, for the second orbit, we have n equals to 2 and when we get this energy. Okay. So this observations show that a photon is absorbed only if it has energy equal to this gap or this gap or this gap or this gap. Actually, this gap has energy difference of 10.2. So the photon having energy exactly 10.2 will be absorbed. This is by observation. Okay, we haven't said anything. We are observing this. The second gap has energy difference equals to 12.1. So we observe that photons of having energy 12.1 are also absorbed. The third has energy gap of 12.75 and we see we can find few more gaps also, but remembering these three data is just sufficient, right? And remember this point, if electrons have energy 10.2, they will I'm saying electron, but I must say photons. So photons are being bombarded and photons are being absorbed. Okay, so what we see, photons will be absorbed if they have energy exactly equal to ground state energy and any of the excited state energy, right? So 10.2 is the energy difference between 1 and 2. So 10.2 photon will be absorbed. 12.1 is the energy difference between 1 and 3. So this will be absorbed. 12.75 is the energy difference between 1 and 4. So this will be absorbed. And obviously the last is 13.6. This is the energy difference between ground state and n equals to infinity. This will be absorbed, and all photons having energy more than 13.6 made to be absorbed. What they do? They just ionize this electron and the remaining energy turns into kinetic energy of that emitted electron. It is just like photoelectric effect. So missing photons. So missing photons have energy equal to 10.2, 12.1, 12.75, 13.6 and all energies more than 13.6. Okay, these photons are absorbed and in the spectrum these photons are missing. Always remember. Okay. So remember few points. Only those photons, I must say photons, are absorbed which have energy exactly equals to difference between energy of ground state and any of the excited state. So why the photon of energy difference between 2 and 3, 2 and 4 are not absorbed? There is reason behind. Actually, the electron has a longest life in ground state only. The orbiting electron has the longest life in ground state only. So if electron is in ground state, then only it grabs energy from photon, okay, because it is the electron that grabs energy from the photon, and the electron always remains in ground state. Suppose because of energy absorption, it goes to some excited state, but it stays there for a very negligible amount of time. So whenever a photon comes, the photon finds electron always in ground state, and as photon finds electron always in ground state, therefore absorption of photon is only possible from ground state. So always remember, electron gets excited to excited levels, but only from ground state. Okay, so absorption is only possible from ground state. Is it not possible that an electron from some excited state to excite to another higher energy orbit? It is obviously possible. It is obviously possible, but the possibility is so rare because in any excited level, electron has not much life. Its life in any excited state level is extremely low. So that therefore, the most of the absorption is from ground state only. So remember this point. So let us say how much energy is required, for absorption. Let us say delta E is the energy required for absorption. So delta E would be actually equal to the energy of nth orbit, where electron is going, where electron is jumping, minus energy of ground orbit, which is equal to actually E1. Okay, E1. So if you put the values, you will find 13.6, because energy is equal to minus times of 13.6 times z square by n square. So we have 13.6. Z square, if we are talking about hydrogen, z is 1. And here we have 1 divided by 1 square, that is 1 minus 1 by n square. So always remember, absorption is only possible from ground state. Okay, and this is the energy required. Now we see emission spectrum. Okay, there is a difference between absorption spectrum and emission spectrum. Okay, so let me explain. Suppose we have a hydrogen gas, and because of absorption of photon or something, the electrons of hydrogen atom got excited into some excited level. Let us say n equals to 3, 4, 5, any level. Okay. Electron go to any higher energy level only from ground state, that you remember, but they come down to ground state directly or by splitting their journey into other states. Say like if some electron is in n equals to 5, but when it de-excites, when it splits energy or it gives energy, it can come down to directly n equals to 1, or it may come down to n equals to 4, like here. It may come down to n equals to 3, it may come down to n equals to 2. So in return, the electron has many more paths possible. Okay, so if from any higher energy state, electron directly jumps to ground state, we call this transition in Lyman series. Always remember, if electron is jumping directly to ground state, all these transitions are called Lyman series. If they jump to n equals to 2, we call it Balmer series. If they directly jump to n equals to 3, they are called Paschen series. If they jump to n equals to 4 bracket, and if they jump to n equals to 5, they are called Pfund series. So as absorption is only possible from ground state, in absorption spectrum we only had Lyman series, but de-excitation or emission of electron is possible to any state. So here we have a lots of series like Lyman series, Balmer series, Paschen series, bracket series, Pfund series, right? Okay. If an electron jumps from any higher energy level to lower energy level, let us say it jumps from m to n, and m is more than n. some energy, the energy equal to the energy difference of these two states is emitted in the form of electromagnetic radiation. So what happens whenever electron jumps from a higher energy state to lower energy state directly, a photon is emitted, and the photon has energy equal to difference of energies of these two. So let me write, the difference of these two energies is actually 13.6 Z square, right? 13.6 Z square. Z is atomic number here, right? Multiplied by 1 by n square minus 1 by m square. Remember, m is more than m, and this is the energy. This is the difference of energy. And this difference of energy is converted into the energy of photon being emitted. Every de-excitation is associated with emission of a photon. And this is the energy of photon being emitted, right? So I can write it as Sc by lambda, as you know, right? So from here we can say 1 by lambda equals to 13.6. Let's convert it into joules, then Z square and divided by Hc. Okay. This constant is further called Rydberg constant, R Z square 1 by n square minus 1 by m square. Okay. And this equation is called Rydberg equation. The value of R is nearly 1.1 times 10 to the power 7 meter inverse. And we should remember this. And this is the Rydberg formula. Always remember, if electron jumps to a high energy orbit from ground state, this is called absorption, and energy required for absorption is given by this formula. Okay, but this is the energy required for absorption. This energy may come from a photon, it may also come from an incoming electron, or it may also come from collisions, the loss of kinetic energy during collisions. So there may be multiple sources of this energy, right? But when electron de-excites to a lower energy state, only electrons are emitted, only photons are emitted, and the photons have energy this, and this is the wavelength of photon being emitted. This is Rydberg formula. Okay. So let us learn Lyman series. Okay. What is Lyman series? When electron de-excites from any level to n equals to 1. So Lyman series means jumping back to n equals to 1. So here 1 by lambda would be equal to R Z square 1 minus 1 by n square. N may take values 2, 3, 4, like this. Okay, if electron jumps from 2 to 1, it is called the first member of Lyman series. If like 2 to 1, it is called first member. If 3 to 1, it is called second member, also sometimes called alpha line. This is called beta line. The 4 to 1 is called gamma line or third member. And if it jumps from infinity to 1, it is called last member, or series limit. Remember, this is very important. Series limit. As this has the lowest energy among all these three. The first member has lowest energy among all these three. It has minimum energy. Minimum energy means smallest frequency, and smallest frequency means biggest wavelength. So longest wavelength. But if we talk about series limit of Lyman, it will be having biggest energy, maximum. It will be having maximum frequency, but it will be having shortest wavelength or minimum wavelength. And also remember one point, if we talk about Lyman series of hydrogen atom, it mostly lies in ultraviolet region. It lies in, for hydrogen, it is in ultraviolet region. So this is about Lyman series. If we talk about Balmer series means jumping back into n equals to 2. Jumping into n equals to 2. N equals to 2 from any place. So the Rydberg formula gives you 1 by lambda equals to r z square, and as it is coming to n equals to 2, oh, I must say n equals to 2. So 1 by 2 square, that is 4 minus 1 by n square. And what is n? N may be 3, 4, 5, etc. From 3 to 2, first member alpha line. From 4 to 2, second member beta line. From infinity to 2, the series limit of Balmer series. And again, the first member has minimum energy, minimum frequency, longest wavelength. And the last member, the series limit, has maximum energy, maximum frequency, and minimum wavelength, that is shortest wavelength. But remember, if we talk about hydrogen atom, this series mostly lies in visible region. Okay. If we talk about Paschen series means jumping back to n equals to 3. So Rydberg formula is 1 by lambda equals r z square, 1 by 3 square, that is 9 minus 1 by n square. N here is 4, 5, 6, etc. And this is in, for hydrogen, this is in infrared region. For hydrogen, it is in infrared. And all other bracket means jumping back into n equals to 4. And this is also in infrared. But I am talking about hydrogen. And Pfund series means jumping back into n equals to 5, and that is also in basically far infrared for obviously hydrogen. Okay, so this is about emission spectrum, and now we will solve few problems based on these series. Here in this question, they say electron collides elastically with an hydrogen atom. And atom's electron actually jumps from ground state to n equals to 3. So what is the energy transferred to the atom? I think you already know the energy difference between ground state and n equals to 3 is simply the energy difference is equal to 12.1 electron volt, as the energy difference between 1 and 2 is 10.2. We have remembered these data. From 1 to 3 the difference is 12.1, and from 1 to 4 it is 12.75. So 1 to 3 the difference is 12.1. So obviously this is the energy gained by atom, and obviously this is the energy transferred to hydrogen atom. So correct answer is A, 12.1 electron volt. Over to next question. Okay. It says the series limit frequency of the Lyman series is VL. So what is series limit? Series limit is the last member, and for last member the frequency is VL. Okay. So as we know, the frequency is given by frequency times lambda is given by C, and 1 by lambda according to Rydberg formula is actually R. As we are talking about hydrogen atom, obviously, so we have Z equals to 1, and the series limit says coming from infinity to 1. So 1 minus 1 upon infinity square. So it is basically equal to R. and 1 by lambda. So lambda can be written as C by nu L. So it is equal to C by nu L. So what we see is the series limit frequency is R times C. Okay, R times C. Now they ask us the series limit frequency of the Pfund series. Okay, series limit frequency of the Pfund series. I think you remember the Pfund series means coming back to n equals to 5. And if you come back to n equals to 5, you have frequency of Pfund series limit frequency of Pfund series divided by C equals to R and 1 by 5 square minus 1 by infinity. So you get R by 25. Okay. And let us divide these two. If you divide these two relations, means you have first nu L by C equals to R, and then you have nu L Pfund divided by C equals to R by 25. Divide these two and you get the required frequency as nu L divided by 25. So B is your correct choice. Okay. Let us move to the next question. Here in this question they say the electron in ground state and nth orbit state have their de Broglie wavelength as lambda n as de Broglie wavelength in nth state and lambda g as de Broglie wavelength in ground state. And they also say, I don't know what is the name of this symbol, let us pronounce it as A. So A and B, the wavelength of the photon emitted in the transition from nth state to the ground state. And also we have to assume that n is a very large number. Okay, so let us select the correct choice out of these four options. So let us solve this. As you know, in every option they haven't used lambda g, they are only using lambda n. Okay, here also they have lambda n. So in every option they are using lambda n. So let us now relate lambda n and this symbol an. Okay, so as lambda n is the de Broglie wavelength in nth state, you already know the de Broglie wavelength in nth state, which is lambda n, is equal to its circumferential length divided by principal quantum number, and circumferential length is actually 2 pi, the radius of nth orbit divided by n, right? The radius of nth orbit is further can be written as 2 pi r naught n square by z divided by n. So we have lambda n proportional to n. Okay, so taking remaining constant as say some constant c, so we have lambda n equals to c divided by, sorry, c multiplied by n. Lambda is proportional to n. Also the wavelength an can be given by Rydberg formula, 1 by an equals Rydberg, and this is the wavelength of photon emitted when transition of electron happens from nth to the ground state. So we have 1 minus 1 by n square, and we have to consider n as to be very large. Okay, so as in every option we have an in the numerator, and in this expression we have an in the denominator. I can convert an as 1 by r and 1 minus 1 by n square to the power minus 1. But as this term, which is 1 by n square, n is very large, so this term becomes very small as compared to 1. So expanding this binomially and taking only two terms, we can write it as 1 by r and 1 plus 1 by n square. And n square can be written as lambda n divided by lambda n square divided by c square, or it will be plus actually. Okay, so we have 1 over r plus 1 divided by r, and n square, at the place of n square we have lambda n square over c square. So this is a constant, c square by r is a constant. So if we consider them a and b, we have a plus b divided by lambda n square, and it is the best match with option C. Therefore, option C is your perfect choice for approximation that n is very large. Okay. Over to next question. In this question, we have the first member of Balmer series of hydrogen atom, and it has a wavelength of 6561 angstrom. Okay. So let me write the result. The wavelength is 1 over 6561 angstrom. Let's say convert this into meter, and we will have 10 to the power 10 in the numerator times equals to R. And as it is the first member of Balmer, means the electron is jumping from n equals to 3 to n equals to 2. Okay. So we will have here 1 over 2 square minus 1 over 3 square. Okay. And they are asking us what is the wavelength of second member of Balmer series. So for second member, the electron will jump from 4 to 2 in the same atom, and I can write 10 to the power 10 divided by 656, the new wavelength lambda dash equals R 1 over 2 square minus 1 over 4 square. If you divide these two and solve for lambda dash, your lambda dash will come out to be 486 nanometers. So this is your perfect answer, 486 nanometer. Okay. Next question. Here they say the energy required to ionize a hydrogen-like ion in its ground state is 9 Rydberg. Let me remind you, the energy required to ionize a hydrogen atom in ground state is actually R times Z square. And as this is given as 9 times R, it simply explains Z equals 3. So we have a hydrogen-like atom whose atomic number is 3. It is basically lithium. And they are asking us what is the wavelength of radiation emitted when electron in this ion jumps from the second excited state to the ground state, means 3 to 1. If the electron jumps from n equals to 3 to n equals to 1, what will be the wavelength of radiation emitted? So let us use Rydberg formula, 1 by lambda equals R, Z square, Z is 3, so we have 3 square, that is 9. And as electron is jumping from 3 to 1, we have 1 minus 1 over 3 square, that is 9. And from here, the lambda would come out to be 1 divided by 9 will be cancelled. We have 8R, we have 8R here. Okay. So now if you have to answer this in nanometer, put the value of Rydberg constant and you will see the lambda will come out to be 11.4 nanometer, nearly 11.4 nanometer. So that is your perfect choice. Okay. So that was a little bit about atomic structure, and now we have to study X-rays. Okay. For many years, X-rays in the syllabus of our examinations, but not many questions have been asked about this. So still, let us understand the few basics of X-rays and then move forward. Okay. So what are X-rays? X-rays are basically a part of electromagnetic spectrum, and when the wavelength of electromagnetic waves is between 0.1 angstrom to 100 angstrom, these electromagnetic radiations are called X-rays. Okay. These are actually highly energetic photons. Okay. No, these are actually highly energetic photons, and they are obtained when highly energetic electrons collide with target atoms. Okay, what are target atoms? So these are basically atoms of a very heavy metal, and when high energy electrons collide with these atoms, with these high heavy atoms, basically the X-rays are produced. Okay, so let us understand the experimental setup, how to create X-rays. So here we again have two electrodes. So here we have a filament, and here we have a copper anode or the target metal. Remember, this should be very heavy metal. So we have copper here. These two electrodes are at a potential difference, and this potential difference gives energy to electrons. So when we heat this filament, the electrons are emitted, and this emission is of thermionic type. We heat the filament and electrons are being emitted, right? And when electrons are emitted, they are accelerated by this potential difference. And as this is extra high tension voltage, it is extra high voltage. So we apply a very high voltage here. So electrons are emitted, okay? And they accelerate when they reach from here to this point, okay? We established vacuum because the vacuum offers free passage to the electrons, and when these electrons strike this target atom, radiations are emitted, and we see these radiations include X-rays. So that is the process. The X-rays are being generated, okay? If we study them further, we divide X-rays into two categories: the continuous X-rays and the characteristic X-rays. The two are different only by their source of origination, okay? Let us understand them one by one. Suppose we have a primary electron beam, incoming electron, very high energetic electron, and they pass through an atom. They just emerge from here, and due to the strong electromagnetic field created by atoms inside atom and nucleus, they bend their path, they lose some of their energy, and what we see, the sum of the energy lost by incoming electron is converted into X-rays, okay? These collisions are of infinite types. Sometimes one electron collides with many atoms, so many types of the energy losses occur in the electron beam, okay? And the radiations emitted are called continuous X-rays, okay? These contains almost all possible kinds of photons. These contains almost all possible kinds of energies. So we have wide range of X-ray due to this, okay? But on the contrary, if the incoming electron interacts with some of the orbiting electron, the incoming electron knocks out the orbiting electron, both electrons are out, it leaves a vacancy in the shell. And if there is a vacancy in the shell, the high energy electron jumps back into the lower energy orbit to fill that gap. And this transition, just like the electron transition in atomic structure, is followed by emission of a photon. And as this is a very heavy metal, the energy difference between two shells is quite large, and as the difference of energy is quite large, the photon emitted too has a very high energy. The photon emitted too has a very high energy that belongs to X-rays. So this is also called X-rays. Here there are not many possibilities of wavelength. So very few, you can say kind of photon are emitted, and these X-rays are actually depend upon the characteristic properties of atom. Therefore, these are called characteristic X-rays. Okay. As I said earlier, the loss of energy of electron may be of infinite types. Okay. At some collision, it loses only 10% of its energy. At some collision, it may lose 40% of its energy. So it is always depends upon circumstances. But suppose some special electron loses its entire energy in only one collision, and only one photon is emitted. This photon will be having the biggest possible energy, and this energy, actually maximum energy of photon, will be equal to actually the incoming energy of electrons, and incoming energy of electron equals to electron times the voltage through which the electron is being accelerated, and this is actually the tube voltage, right? As you know, the photon's energy is written as Sc by lambda. We can write the wavelength equals Hc divided by EV tube. As this is the maximum energy, so this is corresponding to the minimum wavelength. This is also called the cutoff wavelength, and we get no photon, no X-ray photon whose wavelength is less than this. So this is the minimum wavelength that we get in the spectrum of continuous X-ray, remember. And if you want to find this numerically, remember Sc equals 1240, and here you have to put simply the tube voltage, because that will be the energy in electron volt, and we can find lambda minimum. Okay, so that is about continuous X-ray and minimum or cutoff wavelength. But if we talk about characteristic X-rays, can you see here? Here the photons are being emitted, and the energy of photon, that is Sc by lambda, is actually equal to energy difference between two shells. Energy difference between two shells. So it is actually equal to E m minus E n. So we can say the electron is being transmitted from m to n. Electron is jumping from m to n, means from a higher energy orbit to low energy orbit. So m is more than n. Okay. So here from here you can say the wavelength of characteristic X-rays is equal to Sc divided by delta E, where delta E is actually the energy difference of two shells of atom, target atom. Okay. Let us understand the classification or the nomenclature. If we have a K shell, L shell, M shell, N shell as first, second and third and fourth shells. Okay. If electron jumps from, if vacancy is created, remember, if vacancy is created in K shell, then it will be filled by either of L shell electron, M shell electron or N shell electron, etc. Right. So the first member is called K alpha line, the second member is called K beta line, and the third member may be called as K gamma line, and all these X-rays are called K X-rays, right? If vacancy is created in L shell, okay, so the first member is called L alpha, the second member is called L beta. First member will be from the transition of electron from M shell to L shell, and the second will be from N shell to L shell. Okay, and we usually ignore other members because the energy decreases, and as energy decreases, we don't count them in X-rays. So usually we get only K X-rays and L X-rays. There are no M X-rays or N X-rays because their energy is so less. We can't keep them under the boundary of X-rays, right? Okay. Now let us understand the graph related to X-rays. Okay. So we have continuous X-ray. As I explained you, we don't get any wavelength less than a certain minimum, and this is lambda minimum. Okay. There is one more thing. We get very few radiations corresponding to lambda minimum, and I must say very few radiations are corresponding to low wavelength. That is why we have low intensity near low wavelength. And also we have very low intensity for very high wavelength, means very low energy photons. We have largest intensity for medium wavelengths. Okay, so that is the approximate curve of continuous X-rays. Okay, and every wavelength above lambda minimum is possible. That is why we get a continuous graph, and that is why we call it continuous X-rays. But why characteristic X-rays? What are characteristic X-rays? So what are characteristic X-rays? You already know. When a vacancy is created in K shell, the electron from L shell or M shell fills this vacancy, and only certain wavelengths are emitted because the certain energy gap between K, L and M shells is converted into photon. So we get only certain wavelengths here. Suppose these are two K X-rays, one is K alpha and K beta. You know that the energy of K beta X-ray would be large, the wavelength of K beta would be small. So this is actually, you can say K beta and this is K alpha, right? Okay. So if we superimpose these two curves, if we superimpose continuous X-ray and characteristic X-ray, we actually get this kind of a spectrum. Okay. So here we are showing K alpha and K beta both. Actually, the peak of alpha is larger than K beta. You must be wondering why. Because energy of K beta X-rays is large. But why the peak of K alpha is large? Because K alpha is more probable. It's very logical. If you have a vacancy in K shell, it's very likely that it is filled by a L shell electron but not by M shell electron. So cases of K beta are very less. That's why even despite having bigger energy, we have low intensity corresponding to K beta X-rays. So this is actually superposition of these two graphs. And now let us solve few problems based on this. Okay. So here they are asking us, electron beam is accelerated by a potential difference V. They hit a metallic target to produce X-rays. It produces a continuous as well as the characteristic X-rays. The whole story is written actually. Lambda minimum is the cutoff wavelength and V is the tube voltage. Okay, and we have to just establish a relation between log of lambda minimum and log of V. Okay, so let us write, as you know, lambda minimum is actually SC by EV. If we take log on both sides, we have log lambda minimum equals to log SC by E minus log V, And now if you see this relation, the variation between this quantity and this quantity is linear with negative slope and positive y-intercept log SC by lambda, and all these qualities are fulfilled by the option B. So B is obviously the correct choice. Okay, next. Here we have the wavelength of K alpha line in the X-ray tube is near about, so we have the wavelength of K alpha line is nearly 0.036 nanometer. Then we have to calculate the difference of energy of level of L shell and K shell. We all know if we are talking about K alpha X-ray, then the electron must jump from L shell to K shell. Okay, and the energy of photon emitted would be equal to delta E equals to EL minus EK, and this is equal to SC by lambda of K alpha X-ray. So this difference is equal to, actually, if we calculate numerically, so I can write SC as 1240 electron volt nanometer and divided by lambda. So lambda we should put in nanometer. We have lambda in nanometer. So we have 0.036 nanometer. We got nanometer cancelled and we have nearly 34.4 kilo electron volt. So this is the energy difference between L shell and K shell, right? This is the energy difference and that is your answer. Let us see what we have next. Here we have to relate these. We are actually frequencies. So this is the frequency of K alpha X-ray, this is the frequency of K beta X-ray, and this is the frequency of L alpha X-ray. Okay, and we have to relate these three. So as you know, this energy corresponds to our energy of h nu k alpha, and this is equal to obviously the energy of L minus energy of k, right? If we talk about this frequency, so h nu L alpha is actually the energy difference between M and L shell. So we have Em minus El, right? If I add these two, we have h nu k alpha plus nu L alpha equals to El will be cancelled out. We will be having Em minus Ek. Okay, and if we consider this frequency of k beta X-ray, obviously the corresponding energy would be h nu k beta, and this will be equal to Em minus Ek, because here electron is jumping from M to K. So Em minus Ek you can write as h times nu k beta. So cancelling this h gives you the result nu k alpha plus nu L alpha equals nu k beta. So this is the required result. Okay, so that was the two major aspects of X-rays. They ask questions either about the cutoff wavelength, the minimum wavelength, or they ask about the wavelength of characteristic X-rays, or they just ask you some theoretical questions. There is one more law related to characteristic X-rays, which is called Moseley's law. And Moseley's law says, remember, Moseley's law says the square root of frequency of a particular kind of X-ray, just choose either k alpha or k beta, you can choose anything, but if you choose suppose a particular kind of X-ray, let us suppose I am choosing only k alpha, and then you take a lot of metals, apply them in the tube one by one and just plot a square root of frequency versus atomic number of different metals. You repeat the experiment with many metals and you see a linear relationship between a square root of frequency and the atomic number of the metal. So the relationship is linear, and if you plot them, you have a square root of frequency and atomic number, and they give you a linear relationship. Okay, so if you join all these points, the graph is linear. The graph doesn't pass through origin, it passes through some other number other than origin. Okay, so we can write it as A times Z minus B. Here A and B are constants, A and B are simply constants, and B is called a screening constant, remember. And one important fact, if you want to remember, you can remember that for k alpha, A equals square root of 3 by 4 RC, where R is Rydberg constant, C is speed of light, and B equals to 1. If you even do not remember this, it doesn't matter, because in every question they will give you the value of A and B, don't worry. Okay, and as here we have frequency, here we have Z, atomic number. So suppose I have seen many times questions like we are comparing the two metals having atomic numbers Z1 and Z2, and for one the wavelength of k alpha line is lambda 1, and for the other wavelength of k alpha line is lambda 2. So what is the relation between lambda 1 and lambda 2 and Z1 and Z2? So as you can see, for k alpha line we have B as 1 and frequency is inversely proportional to wavelength. So obviously lambda 1 by lambda 2 is square root of lambda 1 by lambda 2 would be equal to Z2 minus 1 upon Z1 minus 1. So this way you can compare the two characteristic wavelength of same kind with respective atomic numbers of the metals. So that was a little about X-rays. Now we will learn nuclear physics. Do you know what the nucleus is? Nucleus is actually the tiny central part of the atom where entire charge and almost the entire mass of the atom is concentrated. Okay. So actually the physics, the phenomena, the reactions where nucleus participates, where nucleus undergoes changes, they are studied under the term nuclear physics, because you know in chemistry all the reactions are at atomic level. Nucleus never changed, but when there are changes at nuclear level, that is actually the nuclear physics. Okay, the radius of nucleus is of the order of 10 to the power minus 15 meter, and this new term is called 1 Fermi. Okay, so the radius is given by, actually the radius is given by R naught a to the power 1 by 3. Remember this point, this is the radius. So radius is proportional to 1/3 root of the mass number, where a is mass number. And if this is radius, remember, if this is radius, okay, if we want to calculate the density of a nucleus, the density of a nucleus will be given by, say, D equals mass of nucleus, total mass of nucleus, let's say capital M, and divided by its volume, right? As all the nucleons, the protons and neutrons are almost equally heavy, let us say the mass of one nucleon is a small m, and there are total of a number of nucleons, means the mass number is a, so the mass of total nucleus would be Ma, and volume would be 4 by 3 pi r cube. But the r cube can be written as r naught cube, and a to the power 1 by 3 is power 3, so it becomes a only. And a cancels from numerator and denominator, and here you see the density is independent of mass number. So if density is independent of mass number, it says that the density of nucleus is independent of mass number, means all nuclei of any atom of any species has almost same density. So the density of all nuclei is almost same, and as it is independent of mass number. Okay, so that's a little about nucleus and its radius and its density. How to represent a nucleus? Okay, so suppose we have an element X, and here we write Z and here we write A. So this is the representation of a nucleus. The Z represents atomic number, which means the number of protons inside nucleus, and A represents the total number of protons plus total number of neutrons inside a nucleus, that is A is called mass number. So if they ask you what is the number of neutrons, so if you represent number of neutrons by n, it would be equal to A minus Z. In nuclear physics, we represent mass by atomic mass units, and one atomic mass unit is approximately equal to this. Okay, by definition, one atomic mass unit is actually the 1/12th part of mass of the carbon 12 atom. Okay, the carbon 12 atom. So atomic mass units are the units in which we represent masses in nuclear physics. Okay, so let's proceed. The next is mass defect and binding energy. Okay, so let us see what is mass defect. It is very surprising to hear that when the different nucleons, means a lot of protons and lots of neutrons, somehow if they are initially at infinite separation and they fuse to combine a nucleus, all the protons and neutrons fuse to combine a nucleus, then what we see, the mass of individual protons and neutrons is higher, and they fuse to combine a nucleus, the mass is decreased, and this decrease of mass is actually called the mass defect. Okay, so that was a mystery how mass is changing, because mass was considered to be conserved. So Einstein solved this mystery, and he said mass and energy are interchangeable. and the mass which is decreasing here is being converted into energy, and it is being released in the form of energy, and the energy released because of the mass defect is called binding energy, because this energy is used to bind the nucleus or all the nucleons together. So always remember, when nucleons fuse to form a nucleus, when nucleons fuse to form a nucleus, energy is released, and this energy is called binding energy, and the source of this binding energy is actually the mass defect. So always remember, mass can be converted into energy, and energy can also be converted into mass. Conceptually, theoretically, if you give this nucleus this energy in a proper manner, or this nucleus will be splitted into the constituent protons and neutrons, and mass will be gained back. Okay, mass will be gained back. So we can convert, or in fact in nature we see examples where mass is converted into energy and energy is converted into mass. Okay, so I think you understood this, and let us now understand the relation, the Einstein relation, through which we can convert mass defect into energy. Okay, so it is the famous Einstein's equation which says energy equals mass defect delta m c square. Okay, so if you have some mass defect multiplied by c square, you get corresponding energy. Okay, so the c square, what is the c square? C is the speed of light. So c square is actually, c square is the square of the speed of light. What is that? It is actually 9 times 10 to the power 16 meter square per second square. Okay, and c square is also 931 million electron volt per atomic mass unit. So always remember, if mass is given in kilograms, if mass is given, if you know the mass in kilograms, you see square as this. And if you do know the mass in atomic mass units, always you see square as 931 million electron volt per atomic mass units, and you get the energy. In first case you get energy in joules, and in second case you get energy in million electron volt. Don't forget that. So we have a question, and it says calculate the binding energy and binding energy per nucleon for iron atom. Okay, so iron nucleus. So as we can see, the iron nucleus has 26 number of protons and 56 number of nucleons. Okay, and nucleons contains what? Protons and neutrons. So if we want to get the number of neutrons, so number of neutrons would be actually the mass number 56 minus 26, that is 30. Okay, they have given us the mass of proton, the mass of neutron, and the mass of the iron nucleus. So what is mass defect? Mass defect is the total mass of all the protons and all the neutrons minus mass of a single nucleus. So let us calculate the mass defect. Okay, mass defect. As we know, there are 26 number of protons. So mass of total proton is 26 times mass of one proton, which is 1.007825, plus mass of all neutrons, and mass of all neutrons is actually 30 times 1.00 and 8665. This is the total mass of protons plus neutrons, and if we subtract the mass of the single nucleus, which is 55.99863, we get the mass defect. I think you can easily calculate this, but what we have to answer is the binding energy, and you know the energy released, or the binding energy, is equal to delta m times c square. But as we know delta m in atomic mass units, the value of c square is 931. So we have this much. We have this much here multiplied by 931. So if you calculate this, you will get 432.7 million electron volt. This is the binding energy of the nucleus. But as they have asked, what is binding energy per nucleon? So binding energy per nucleon is actually the total binding energy divided by the mass number. So if we divide total binding energy 432.7 divided by mass number, which is 56, you get binding energy per nucleon as 7.73 million electron volt. So this is the contribution by each nucleon into the total binding energy. Okay, so let's move ahead. We have next question as they are asking us what is energy equivalent to 0.5 gram of a substance. Okay, so if we have 0.5 gram of substance, by using Einstein's mass energy equivalence, we know the energy equals mc square. We have mass as 0.5 gram, that is 0.5 times 10 to the power minus 3 kilograms. And if we know the mass in kilograms, the value of c square is 9 times 10 to the power 16. And the answer must be in joule. So calculate this and you will get 4.5 times 10 to the power 13 joule. And that is why the C is your perfect choice. Okay, so let's move for next question. This question says the graph which you have to choose the graph which depicts the result of Rutherford's gold foil experiment with alpha particle. So I think you all must have studied that, okay? And the basic result of that experiment is the most of the alpha particles, almost all alpha particles are deflected, are not deflected at all. So deviation for most of the alpha particle is almost zero, and only this graph shows this. This is actually deflection, and here we have zero, and only this says lots of alpha particles, because this is very high. Lots of alpha particles have almost zero deflection, and only few alpha particles have deflection non-zero. So this is the perfect graph, and correct answer is this. In rest of the questions, obviously, if you see B and D, it says almost negligible number of particles are deflected by zero deflection. So that is obviously wrong. Okay, and obviously the number of alpha particles deflecting and deflection angle has no linear relationship. So this is also incorrect. So correct choice is obviously A. Okay, so now we will talk about stability of a nucleus. The first thought that comes to our mind is greater is the binding energy, greater is the stability. But if we compare the stability or binding energy of two nucleons, say nucleus, say one has 20 nucleons and one has 200 nucleons. Suppose this has binding energy equal to 50 million electron volt, and this has binding energy equal to 100 million electron volt. Obviously, if you compare, obviously this has more binding energy, but as you see the size of this nucleus, which is so big, the binding energy contribution because of each nucleon is only 0.5 million electron volt, while here we have almost 2.5 million electron volt energy associated with each nucleon. So obviously this is more stable than this, and by this argument we understand the binding energy per nucleon is a better criterion for stability. So always remember, bigger is the binding energy per nucleon and the greater will be the stability. So stability, you can say, is directly proportional to binding energy per nucleon. Okay. If we draw the binding energy per nucleon curve with respect to mass number of many elements, and you must have seen in many books, the curve looks like this. Okay. The iron has biggest binding energy per nucleon, so this is most stable, and here we have hydrogen, tritium, helium, lithium, etc. And as you can see, when we look at light nuclei, the binding energy per nucleon is less. And when we look at very heavy nuclei, the graph again dips down, so binding energy per nucleon is less, right? So I'm showing you a few conclusions that we can draw from this curve. The first is light as well as heavy, both kinds of nuclei are generally unstable. As you can see here, the light nuclei too have less binding energy per nucleon, the heavy nuclei too have less binding energy per nucleon. Only the middle sized nuclei have greater binding energy per nucleon. So light as well as heavy, both are unstable, right? The second thing, the nuclei for which we have even number of nucleons, or you can say equal number of protons and equal number of neutrons, they are slightly having bigger stability with respect to their neighbor because of the better packing. When we have equal number of protons and equal number of neutrons, they are more strongly packed, they are more you can say tightly packed inside nucleus, and we get better stability as compared to the nucleons which have different number of protons and neutrons. Okay, in case of light nuclei, remember. Okay, the next point, you can easily see from graph that if two light nuclei combine, that when two light nuclei combine, they can form a middle sized. If two light nuclei combine, they can form a middle sized nuclei. And if two light nuclei are combining to give a middle sized nuclei, and binding energy per nucleon is increasing, this process releases energy, and this reaction in nuclear physics is called fusion reaction, where two very light nuclei fuse to combine and give a bigger nuclei. This is called fusion reaction, and here also the energy is released, as can be seen by this equation. Here we have four hydrogens, and four hydrogens are fusing in each other to form a helium atom, right? A helium nucleus, and 25 million electron volt energy is released. Actually, we have to write 4 here. So 4 is actually mass number and 2 is atomic number of helium nucleus. Okay, so this is called fusion reactions. But nature has another way of getting stability for big nuclei. So suppose we have a big nuclei here, it has lesser binding energy per nucleon, but when it splits into two or more mid-sized nuclei, then obviously those mid-sized nuclei would be somewhere here, and if they are in this range, in this region of the graph, obviously binding energy per nucleon increases, and if binding energy per nucleon increases, the energy is again released, and this type of reaction is called fission reaction in nuclear physics. Okay, and a very good example of fission reaction is shown here, where uranium, when bombarded with neutrons, is splitting into barium and krypton. Okay, and here also energy is being released. Okay, next, now we have a very important term numerically in nuclear physics, and that is Q value of a nuclear reaction. What is a Q value? If you take example of a particular nuclear reaction, and the Q value would be the net energy released in that nuclear reaction. So it is the net energy released. It's a very simple concept, and it is the net energy released during a nuclear reaction. So how to calculate Q value? I have already told you that the source of nuclear energy is actually the mass defect. Okay, so Q value can be written as mass defect multiplied by C square. That's very simple, as if mass of reactant is more, mass of product is less, that's where we can say the mass is decreasing, and if mass is decreasing, the decrease of mass times C square is Q value. That is the first formula. Then if we are given, if we are not given the masses, but we are given the binding energy of all the elements, then binding energy of product minus binding energy of reactant is simply the Q value. Okay, and in terms of kinetic energy, obviously if the kinetic energy of product is more, kinetic energy of reactant is less. definitely the energy is in the form of kinetic energy. Then kinetic energy of product minus kinetic energy of reactant is actually the Q value. So which formula do you apply? It depends upon the information of the question. If they give you masses, use the first formula. If they give you binding energy, use the second formula. And if they give you kinetic energy, use the third formula for getting the Q value. Okay. So let us solve few problems based on Q value. Here we have a graph, and this graph, it's a binding energy per nucleon graph, and this graph is binding energy per nucleon versus mass number. This is mass number 20, 40, 60. 60 is for Z, 20 is for X actually, and it is written here, so it's not visible, I think. So 20 for X and 40 for Y. Let me write it here. Okay. For X, the binding energy per nucleon is 3. For Y, it is 5. And for Z, it is 7. So let us check the binding energies of X, Y, and Z. Okay. For X, binding energy of X. Okay. As you know, binding energy per nucleon of X is 3, but there are 20 nucleons. So binding energy, total binding energy would be 20 multiplied by 3, that is 60. So for X, binding energy is 60. Binding energy for Y is obviously 5 times 40, and 5 times 40 is 200 million electron volt, and binding energy for Z is definitely 7 times 60, and 7 times 60 is 420 million electron volt. Now they are asking us what is the Q value of the following reactions. So let us take the Q value. As we know the binding energy, we will apply the second formula, binding energy of product minus binding energy of reactant. Okay. So what is binding energy of product? If we see X and Y are product, so Q value for the first part is going to be the binding energy of X plus binding energy of Y, that is 60 plus 200, that is 260, minus binding energy of reactant. So reactant is Z, so binding energy of reactant 420, and you can easily see the binding energy is actually minus, let me write it here, minus 180 MeV. Okay, so this minus sign says this equation is not feasible, or you can say this equation is endorgic. So always remember, if Q value of a reaction is negative, this is called endorgic. As you must have said in chemistry, exothermic, endothermic reactions. Here in nuclear physics, we say exorgic and endorgic. So as the Q value is negative, this reaction is endorgic. Let me write it here. Endorgic. Okay. B. So Q value for reaction B, for option B, is binding energy of product minus binding energy of reactant. Here we have 3Y. 3Y means Y, for binding energy of Y is 200. So 3Y would be 600 minus 3X. So 3X, how much is 3X? 3X, X binding energy is 60. So 3X would be 180. Plus Z, and Z is 420. So let me write it as 420. Okay. So if you calculate this, you get binding Q value as 0. It means no net energy is being released in reaction 2. This reaction again is of no use if we want to use the reaction produced by the energy produced by the reaction. And if we talk about the third option, C, the result is 2Z. So the binding energy of product is 2Z, and 2Z would be 840. Twice of 420 is 840 binding energy of product minus binding energy of reactant. Here we have 4X. So 4X is 240 and Y is 200. So plus 200. And if you calculate this, you will have 840 minus 440, we have 400 million electron volt left as the energy released. Okay, so this reaction is exorgic. So remember these points. Okay, let's move for next question. Here we have a reaction where four helium particles are combining to give a oxygen particle, right? And they are asking us what is the net energy released. If you see clearly here, masses are given. If masses are given, we have to use the formula for masses, okay, for finding Q value. As you know, the Q value of a reaction is equal to mass of reactant minus mass of product times C square. Okay, so mass of reactant, as we have four particles of helium. Okay, so as we have four particles of helium, we have a mass of reactants at 4 times mass of helium particle, which is 4.0026 minus mass of product. So product is 1 particle of oxygen and the mass is 994. Yes, and C square, as the mass is expressed in atomic mass units, C square would be 931 million electron volt per atomic mass units. And after all calculations, you will see the Q value of the reaction would be 10.24 million electron volts. So in each of this reaction, per reaction, this much energy will be released. Okay. The next question. The next question says a nucleus with mass number 240. Let's take the nucleus as X and its mass number is 240 and it breaks into 2 fragments. It is a example of fission reaction. So it breaks into 2 fragments, each of mass 120. Okay. So let us say it breaks into A plus B and each have masses, mass numbers 120 each. The binding energy per nucleon of unfragmented nuclei means this is 7.6. 7.6. This is the binding energy of X and fragments binding energy is 8.5 MeV. So 8.5 MeV. And they have asked us what is the total gain in binding energy in the process. The gain in binding energy is obviously the binding energy of product minus binding energy of reactant, and that's also the Q value. Okay, so actually the gain in binding energy, delta binding energy, would be simply the binding energy of product. So as we have same binding energy for the 2 fragments, this is 120, this is 120, we can say the binding energy of product is 240 times 8.5 minus binding energy of reactant would be 240 times 7.6. If you take 240 common, so 240 and we'll be having 0.9 here. Okay, and if you multiply this, you will be having 216 million electron volt. So obviously D is your perfect choice. Okay, let us see what we have next. So now we have types of radioactive decays. Till now we have seen there are 2 types of methods in which particles achieve stability. One is fission reaction and one is fusion reaction. But there are other methods also, and the one of them is radioactivity. The nuclei, many nuclei emit particles, emit elementary particles like alpha particle, beta particle and gamma particles, and by emitting these particles they reduce their energy and gain stability. Okay, so the first type of decay is alpha decay. Actually, emission of these elementary particles is called radioactivity. Remember, the emission of these elementary particles, alpha, beta, gamma particles, is called radioactivity. And the particles, the nuclei which emit alpha, beta, gamma particles are called radioactive particles or radioactive nuclei. So the first kind of decay is alpha decay. What is an alpha particle? You all know that alpha particle is actually a helium nucleus. Alpha is a helium nucleus having mass number 4 and number of protons 2. That is number of neutrons also 2. Can you see it has 2 protons and 2 neutrons? So helium is very tightly packed particle, and its stability is also very high as compared to its neighbors like hydrogen, lithium, etc. The helium has extraordinary high stability because of the structure of helium atom, right? Okay, and that is why helium is commonly used for bombardment in nuclear reaction. Okay, so alpha decay usually happens when the mass number is more than 210. Okay, alpha decay usually happens when mass number is more than 210. Okay, so what happens when alpha decay occurs? Suppose we have an element X whose mass number is A, atomic number is Z, and it splits or it emits an alpha particle. Where it emits an alpha particle, the remaining nuclei changes. So let us say that this is Y. Obviously, it emits an alpha particle. An alpha particle has 2 protons and 2 neutrons. So total number of nucleon is 4. So as 2 protons are released, the Z is converted to Z minus 2 because there are the 2 protons are missing. It is Z minus 2. And as 4 nucleons are emitted, we have mass number of this particle as A minus 4. In nuclear physics terminology, this is called parent nuclei and this is called daughter nuclei. Okay, this is generally at rest, and when alpha particle shoots up, the daughter nuclei recoils back because of conservation of momentum. Okay, so suppose the alpha particle has kinetic energy K alpha and it goes in certain direction like this. The kinetic energy of this particle Y can be written as Ky, and the Y is recoiled back in opposite direction of motion of alpha particle. Always remember, and as the initial system was at rest, the momentum will still be 0, and that is why the 2 particles Y and alpha will be having equal momentum. As you know, the momentum can be written as square root of 2 mk to mass. The mass of Y would be A minus 4, the mass number times mass of 1 nuclei times Ky. This is the momentum of daughter nuclei, and the momentum of alpha particle would be twice of 4m because mass number is 4 and K alpha. If you square on both sides, cancel common terms, you will have K alpha upon Ky as A minus 4 by 4. That is equation number 1. And as you know, if we have kinetic energy K alpha, Ky, they are the product, and kinetic energy of reactant is 0 because it was at rest. The Q value of the reaction is kinetic energy of product K alpha plus Ky minus kinetic energy of reactant, which is 0. This is the second equation, second very important equation. And if somehow by any of the 3 methods, in fact 2 methods explained before this, if you know the Q value or they directly give you in question the Q value, you can calculate the kinetic energy of alpha particle and kinetic energy of daughter nuclei using these 2 equations very easily. Okay, and the next very important thing is, as if you have a fixed value of Q, K alpha and Ky will be having unique values, and if K alpha and K alpha and Ky have unique values, in all reactions every alpha particle will be emitted with equal energy, and it can be verified also. How it can be verified? Suppose we have this sample, this radioactive sample emitting alpha particle. So suppose in this direction lots of alpha particles are being emitted. we somehow converge all alpha particle into a single beam traveling in same direction. And if now they enter a magnetic field, a perpendicular magnetic field, perpendicular to velocity of alpha particle, they all go in circles. And we see equal radii of circle for each particle, and this equal radii ensures equal momentum because R equals mv upon qb. So equal radii ensures equal momentum, equal speed and equal energy. That confirms every alpha particle is emitted with equal kinetic energy. Okay. So we have this question. Let us solve this. This says a nucleus with mass number 184 initially. We know that the alpha particle is emitted when mass number is usually more than 210, but if they are saying it, we have to believe this. So the nucleus which is initially at rest emits an alpha particle. So say we have a nucleus X of mass number 184. It is converted to Y and it emits an alpha particle. Alpha particle has mass number 4, the Y has mass number 180. Obviously, they both move in opposite directions. And as I told you, K alpha upon Ky equals A minus 4, which is 180, divided by 4, and this is equal to 45. Right? And also the Q value of the reaction is 5.5 MeV. This is already written. So we have Q value as 5.5 equals K alpha plus Ky. Find the Ky from here and put it here. You know the value of K alpha. And the K alpha will be around 5.4 million electron volt. So if you check all the answers, obviously the D is perfect choice. Okay. So that was this question. Next we have beta decay. Beta decay are actually of two types: beta minus decay and beta positive decay. Beta negative, this particle beta minus is actually an electron, is simply an electron, and beta positive is basically a positron. Positron, what is a positron? Positron is an antiparticle of electron. It has same mass as electron but charge equal and opposite to that of electron, that is equal to the charge of proton. Okay. But the beta minus decay, the electron that you see in beta minus decay is not a ordinary electron that revolves around nucleus. This electron has come from inside of the nucleus. Now you will say, okay, how can electron come from a nucleus when nucleus has no electrons at all? So what happens inside nucleus? Inside nucleus, a very high, if nucleus has very high energetic neutron, so very high energetic neutron makes nucleus unstable. So this neutron is sometimes converted into proton. By charge conservation, an electron is also produced and one more particle is produced. One more particle is produced and it was named anti-neutrino. This is called anti-neutrino. Okay. This is inside nucleus, this is inside nucleus, so they are almost at rest. And these two escape from nucleus, obviously in opposite direction to conserve momentum. Okay. And kinetic energy of electron plus kinetic energy of anti-neutrino is equal to actually the Q value. But as for the case of alpha particle, the ratio of electrons energy and ratio of antineutrinos energy is not fixed. So they too can take any value. The kinetic energy of electron may be 0, and if kinetic energy of electron is 0, the kinetic energy of neutrino is Q. If this is 0, it is Q. They both can be Q by 2, Q by 2. The both can be Q by 4, 3Q by 4. So any type of values they can take, and it is purely coincidental. Okay. So what we can say, the range of kinetic energy of electron and the range of kinetic energy of antineutrino both is 0 to Q, 0 to Q, but their sum is equal to Q. Okay. What happens when a beta positive decay occurs? When a beta positive decay occurs, a very excited proton, which makes the nucleus very unstable, is converted into a neutron, and anti-electron means positron. And here also a new particle is emitted, and this new particle is called neutrino. Here also the kinetic energy of positron plus kinetic energy of neutrino is equal to Q value of the particle, and here too we get the similar type of result, means the ratio of positron and this neutrino is not fixed. So here also we get similar types of result. Okay. So this is about radioactive beta decay. When this happens, let us understand what are the changes in the nucleus. Okay. So suppose a particle X, a nucleus X having atomic mass number A and Z, gives a beta minus decay, means electron decay. So when beta minus decay occurs, it is converted into a daughter nucleus Y. The mass number isn't changed. Mass number isn't changed because the neutron is converted into proton. And if neutron is converted into proton, the number of nucleon is fixed. And if number of nucleon is fixed, the proton stays inside the nucleus. So you can say the mass number is same, but the atomic number increases by 1. So Z becomes Z plus 1. The place of this element in Mendeleev's table shifts by 1. Okay. To the right, obviously, because if 2 protons were decreasing in alpha decay, the place shifts to 2 place left. But here the place shifts 1 place towards right. 1 electron is emitted and 1 antineutrino is emitted. That is the reaction. So mass number remains the same and atomic number increases by 1, remember. But when beta positive decay occurs, as proton is converted into neutron, again there is no change in mass number, but Z decreases by 1 because 1 proton is missing. Now positron comes out of the nucleus and neutrino also comes out of the nucleus. Okay. So this is a little bit about alpha decay and gamma decay. And now we have alpha decay and beta decay. Now we have the third type of decay, which is gamma decay. Gamma is actually you can say electromagnetic radiation. Okay. So whenever alpha and beta decay occurs in nucleus, after the emission of alpha and beta decay, atom gets excited, the nucleus gets excited, and when it returns to its ground state or lower energy level, this energy, the difference of energy is emitted in the form of electromagnetic radiation. And this radiation has energy in the range of million electron volt. That is why we say this radiated energy as gamma photon, because it has similar energy with respect to gamma photon. So these are the 3 decays, alpha, beta and gamma decay. Let us solve few questions based on these. So we have first the atom. We have an atom of mass number 15 at an atomic number 7, and it captures an alpha particle and then emits a proton. Okay. So we have a particle nucleus X mass number 15, atomic number 7. It captures an alpha particle. So it captures an alpha particle which has 2 protons, 2 neutrons. And then it emits a proton. It says it emits a proton. So mass number of atomic number of resulting atom will be nearly. Okay. So let us see. Suppose it is converted into Y plus 1 proton. Okay. So here we have 7 plus 2, 9 protons, and here we have 1 protons. So remaining 8 protons must be here. And here we have 15 plus 4. How many? 19 nucleons. Here we have 1 nucleon. So the remaining 18 nucleon must be here. So mass number and atomic number of the atom should be 18 and 8. So D is your perfect choice. There is no doubt about it. Next. Here it says a radioactive nucleus undergoes following decay. The X is converted to B and B is converted to C and C is converted to D. But if you see this, when X is converted to B, 1 proton is missing. And when 1 proton is missing, you know a beta positive decay occurs. Okay, so first particle that is emitted is beta positive. Then you see in second decay, 2 protons are missing. If 2 protons are missing, alpha particle takes 2 protons away. So the second particle emitted is an alpha particle. And after that, you can see 1 proton is increasing. And if 1 proton is increasing, now you know that it is a beta negative, beta minus decay. So the third particle is beta minus decay. And the correct sequence is obviously C. So C is your perfect choice. Okay, let us see what we have next. Here we have a uranium isotope 23592 and it is bombarded with a neutron. So U23592 is bombarded with a neutron and then it generates this particle Kr 8936, another particle say X and 3 neutrons. So 3 neutrons means 0, 1. And if we balance the equation, we have actually 236 nucleons here. If we have 236 nucleons here and here we have 89 plus 3 means 92. So if we subtract 236, 92, we have 4, we have 13 minus 9, 4 and we have 144. So the remaining 144 nucleons must be here because there is no other place to go. Yes, and if we look at protons, there were total of 92 protons. And now here we have only 36 protons. So where are the remaining? They are with X. So 92 minus 36 is actually 92. What is 92 minus 36? 92 minus 36 is 56. So here we have 56. And if you check, your B is correct choice. So the perfect answer is B. Next question. In this question, they say in a radioactive decay chain, the initial nucleus is thorium 23290 and at the end there are 6 alpha particles and 4 beta particles which are emitted. Always remember when they do not say whether it is beta positive or beta negative, you have to consider always beta minus because by default beta particle is electron. Okay, remember this point. So you don't have to assume beta positive by yourself. If they say it is beta positive, then assume beta positive. If they do not say anything, assume always beta minus. So we have 4 beta particles and 6 alpha particles. Let us see what change it is going to make in the initial element. So initially we have thorium 232 and 90. If it emits 6 alpha, in 6 alpha, 12 protons and 12 neutrons must be missing. So if we reduce 12 protons from here, we get X, and 90 minus 12 gives you 78. Okay. And 12 protons, 12 neutrons means 26 nucleons, 26 mass number. 24 mass number. So 232 minus 24 gives you 208. 208. But as there are 4 beta particles also emitted, so if this further emits 4 beta particles, when beta particles are emitted, there is no change in mass number. So mass number is still the same. With Y, mass number is same, 208. But in every beta particle, beta minus decay, the mass number increases by 1. So by 4 beta particle decay, the atomic number increases by 1. So in 4 beta particle decay, the atomic number must increase by 4. So here we must have 82. And if you check these values, you will see the option A is your perfect choice. Now we know what is radioactivity, but we should always remember radioactivity is a spontaneous and completely random process. So if you have n number of nuclei which have all equal probability of decay, but who will decay, which particle will decay, nobody knows. Only we can predict that how many of them can decay in a certain interval of time, and those laws are the purpose of studying this further topic, the radioactive laws. So we have the Rutherford-Soddy's law, and this law tells us how many decay will occur if you have a certain amount of sample with you. But let us first understand what is radioactivity numerically. So if you have a radioactive sample X and it is decaying into Y by any of the decay like alpha, beta or gamma decay, and it is being converted into Y. So if initially we have n naught number of nuclei of X and 0 nuclei of Y, and if any piece of time, say t, the number of nuclei of X now becomes n. If these are n, obviously Y would be n naught minus n, because the difference is converted into what? Y. So now we know the X is regularly or continuously decaying. So the decay rate of X is called minus dn by dt. We have used minus sign here because n is decreasing, and this is called decay rate or rate of disintegration or activity or radioactivity. So always remember this is decay rate or rate of disintegration or activity or radioactivity. The SI unit for decay rate or activity is DPS. DPS. It represents decays per SI unit, and it represents decays per second. We have other units also, but the most important and most popular unit is DPS. If they use any other units, usually they mention the conversion factor in the question itself. Okay, so you don't have to remember everything. So let us learn what is Rutherford-Soddy law of radioactivity. But always remember one thing: this law works only if the initial number of nuclei or number of nuclei at any time is very, very large. So it works with large number of nuclei. And the law says The law says the rate of disintegration of a radioactive nuclei is directly proportional to the number of nuclei present at that time. So as you can see, at time t, the decay rate is minus dN by dt, and at time t, the number of nuclei present for x are n. So this is directly proportional to n. So the law says minus dN by dt is proportional to n. If I use a proportionality constant, this becomes minus dN by dt equals lambda n, where lambda is called decay constant. Lambda is decay constant, right? Remember, lambda is called decay constant. As this is activity, it is it is activity. So always remember, activity is also called lambda n. So activity, if we have activity, so activity is either minus dN by dt or simply multiplication of decay constant and number of nuclei present at that moment. So if n is variable, activity also varies, dN minus dN by dt also varies. Okay, if we manipulate this a little, we have dN by n on the left and minus lambda dt on the right, and if you integrate this, you have at t equals to 0, say n naught nuclei of x, as we have seen in the last page, and at time t we have n number of nuclei of x. By integrating this, you get a result that n equals n naught e to the power minus lambda t. So this is number of nuclei of x present at any time. As activity is also a function of time, so activity at time t is actually equal to lambda times n. And if you multiply lambda by n, n is this, you get lambda n naught e to the power minus lambda t. And lambda n naught is actually can be called initial activity or simply A naught. You can replace lambda n naught by A naught. Always remember these two laws. These are very important. This is for number of nuclei present now at time t, and AT is activity after time t. Half-life and average life. Half-life is actually the time span in which half of the particles, half of the nuclei are decayed or half of the nuclei are left. So half-life is represented by letter T, and average life here is just similar to the time constant, like we studied in discharging of capacitor or decay of current in LR circuits. So it is simply similar to time constant. In one time constant or in one average life, the amount of substance remained is only 1 upon E times of the initial amount. Okay, so always remember, if we have initially n naught nuclei at t equals to 0, at t equals to capital T, that is half life, the number of nuclei remaining are n naught by 2, and at t equals to tau, that is half life, the number of nuclei remaining equals to n naught by E. Okay, I think you remember it is nearly 0.37 times of n naught. Okay, so these are the meanings of half-life and average life. Suppose in a certain time interval there are n half-lives. Remember, if in a certain time interval there are n half-lives, so I can represent that time equals to n times half-lives, and if I replace t by nt in this formula, you get another formula of n, the undecayed element, as n naught divided by 2 to the power n. So always remember one thing, when you know time, use this as the main formula for finding undecayed particles. And if you have time in terms of half-life, in integral multiples of half-life, you can use number of half-lives as n, and this is the formula for number of undecayed particle at time t. Okay. So let us solve few problems based on this. The first problem says half-life of radium is 1600 years. So if half-life of radium is 1600 years, what is the fraction of sample undecayed after 6400 years? Okay. So in this example, you can see this is a fourth multiple of this. So you can say in 6400 years, there are 4 half-lives. So n equals to 4. N equals to 4. And if n is 4, number of undecayed particle equals to initial number of particle divided by 2 to the power n, which is 4. So it is equal to, you can say n by n naught, means the fraction required is 1 by 2 to the power 4, which is 1 by 16. So correct choice is A. Isn't this? Okay. Let us move to next problem. Here we have another problem and it says for a radioactive material, half-life is 10 minutes. And if initially there are 600 number of nuclei, if initially there are 600 number of nuclei and the half-life is what? 10 minutes. The time taken for the disintegration of 450 nuclei. Remember, if the 450 nuclei have been decayed, the number of nuclei undecayed are 150. So if we use n equals to n naught divided by 2 to the power n, the number of undecayed particle as 150 equals to 600 divided by 2 to the power n. We can see 2 to the power n is 4. And if 2 to the power n is 4, n equals to simply 2. Means 2 half-lives. The time is comparable to 2 half-lives. So as the half-life is 10 minutes, 2 half-life span would be 20 minutes and C is your perfect choice. Let's move to next question. This says half-life of a radioactive nuclide is 100 hours. Again, it's very similar question. The fraction of original activity that will remain after 150 hour. Okay, the fraction of original activity that will remain after 150 hour. So in 150 hour, you can say there are 1.5 half-life. So number of half-life in 150 hours is 1.5, and as A can be written as A naught divided by 2 to the power n, which is 1.5, it can be written as A naught divided by 2 root 2. So the perfect fraction is 1 over 2 root 2, a very similar question to the first. Okay, and let's move to the next one. Here we have to calculate something. Always remember one point. The average lifespan, the average life is bigger than half-life, because in average half-life the number of undecayed particles are less. So average life is more than half-life. So what we have here? Okay, here we have a radioactive nucleus A with half-life T, and it decays into B. Okay, at T equals to 0, let us assume the A is n naught and there is no B according to question. But after time T, let us assume the remaining particle of A is n, and as the ratio of number of particles of B and A is given as 0.3, you can say the number of particle of B would be 0.3 n. And as the total number of particle has to remain same, A is being converted into B, but total has to remain same, you can say the sum of these two, 1.3 n equals n naught. So now we know what is n, right? Okay. So as you know, the n equals n naught e to the power minus lambda t. I should place at time t, the n is n naught divided by 1.3. So n equals n naught divided by 1.3. And after flipping, you have e to the power lambda t equals 1.5. taking log on both sides and by putting lambda equals to ln2 by t half, you can easily calculate half-life, and your half-life will come out to be t times log 1.3 by log 2. So option C is your perfect choice. Let us see what is next. Here we have a sample of radioactive material A that has activity of 10 millicurie, and the sample of material B has 20 millicurie. The sample of material A has twice the number of nuclei as another sample of a different radioactive material B. So if we have A and B, let us say their decay constants are lambda 1 and lambda 2. Their initial number of nuclei are n naught and 2n naught, as they say. The A has twice the number of nuclei of another sample B. Okay. So as they say, the activity is 10 millicurie. So as activity is lambda times n. So let me write activity, which is 10 millicurie, as lambda. What is lambda? Lambda 1 times 2n naught and 20. The second particles activity as 20 equals lambda 2 times n naught. If you divide these two, you will have 10 by 20 as 1 by 2 and 2 lambda 1 upon lambda 2. So 1 by 2 equals 2 lambda 1 by lambda 2. So we have lambda 2 as 4 lambda 1. Lambda 2 as 4 lambda 1. And as half-life is reciprocal to lambda, we have half-life of 1 equals 4 times half-life of 2. So the first sample's half-life must be 4 times of the half-life of second. So C is your perfect choice because the ratio of 2 half-life is 4, and this ratio is not same in any of the other options. So option C is your perfect choice. Let us see what we have next. Yes, here they say at a given instant, say at t equals to 0, the two radioactive substances have equal activities, and the ratio of their activities after time t is e to the power minus 3t. Then if half of life A is ln2, then what is half life of B? Okay, so let us solve. Let us say one element is A and other element is B. It has decay constant lambda 1, it has decay constant lambda 2. It has initial number of nuclei as n naught 1 and it has n naught 2. And as the initial activity is same. Okay, so I can write initial activity as A naught and initial activity of B also as A naught, right? As RB over RA is e to the power minus 3t, I can write RB as A naught e to the power minus lambda 2t and RA as A naught e to the power minus lambda 1t, and that's equals to e to the power minus 3t. A naught got cancelled and you can easily write lambda 2 minus lambda 1 equals 3. Okay. Now see, if half-life of first element is log 2, ln2, I can write lambda 1 as ln2 by half-life ln2. So lambda 1 is 1. From here you can see lambda 2 will be 4. And as lambda is ln2 by half-life, which is t2, T2 is simply ln2 by 4, and if T2 is ln2 by 4, option A is your perfect choice. Okay, next question. Okay, here we have a nuclear counter, and nuclear counter counts the rate of emitted particles per second. And what is rate of emitted particles per second? It is activity. So nuclear counter here counts activity, right? And it says at t equals to 0, activity was 1600, and after 8 seconds it is only 100. So activity 2 decays exponentially. I can write the activity A as A naught divided by 2 to the power n, as the recent activity is 100 and initial activity is 1600 divided by 2 to the power n, you see 2 to the power n is 16. And if 2 to the power n is 16, n equals to 4. So in a span of 8 seconds, there must be 4 half-lives. And if there are 4 half-lives, the each half-life is simply 2 seconds. That's simple. So you can say the half-life is 2 seconds. Now they say what will be count rate after 6 seconds. So after 6 seconds, you can say activity will be equal to initial activity 1600 and divided by 2 to the power 3, as in 6 seconds there are 3 half-lives. And this will be 1600 upon 8, that is 200. So 200 is the activity and C is your perfect choice. Let us see what we have next. This question again very simple, and it says the radioactive substance decays to 1/16th of initial activity in 80 days. So if it decays to 1/16th of its initial activity in 16 days, you can say 1 upon 2 to the power n is 1/16. So n is 4. So there are 4 half-lives in 80 days. And if there are 4 half-lives in 80 days, the one half-life will be simply 20 days. So 20 is your perfect answer. Okay, let us move for next and last question of today, which is this. And it says log of activity is decreasing with time as shown in the figure. Okay, so let me write the law of activity. You know the activity is given by initial activity e to the power minus lambda t. If you take log on both sides, you have ln r equals to ln r naught minus lambda t. And you compare, if you compare this equation with this graph, the graph between ln r and t is obviously a straight line with negative slope, right? And the slope, the magnitude of slope is simply lambda. So if you find the magnitude of slope here, you have perpendicular as 6, base as 40. So 6 divided by 40 is your lambda. And lambda you know already is ln 2 divided by half-life. So your half-life becomes 40 times ln 2 by 6. And if you calculate it, it will be nearly 4.62 seconds. So D must be your perfect answer. So that's all for today. I hope you have enjoyed this session. Always see all sessions given by me in steps of not more than 1 hour, and you will maximize your learning. I wish you all the best for your exams. Thank you. Thank you so much. Thank you so much.